Have you ever noticed how often we think about endings? We wonder how a movie will finish. We skip ahead in a book to see the last page. We ask how a relationship will turn out. And at some quiet moment, maybe late at night like this, we ask a much bigger question. How does everything end? Not just our own lives, not just our planet, but everything. The stars, the galaxies, the universe itself. It's a strange thing to think about. The universe feels so large, so steady, so far beyond us. When you look up at the night sky and see stars scattered across the darkness, it doesn't feel fragile, it feels permanent. But is it? Why do we even care? Humans have always imagined the end of the world, long before telescopes, long before science. Ancient stories spoke of floods covering the earth, of fire raining from the sky, of gods resetting creation like wiping a chalkboard clean. In many cultures, the world ends in flames. In others, it freezes. In some stories, it collapses and is born again. So where did this obsession come from? Part of it is simple. We know that things end. We see it every day. A candle burns down. A tree grows old and falls. A pet grows quiet and passes away. Even mountains slowly wear down, grain by grain, like sand slipping through fingers. Nothing around us lasts forever. So naturally, we look at the biggest thing we know, the universe, and ask the same question: will it also end? It might seem strange to compare the universe to a candle. The universe is about 93 billion light years across, so wide that even if you could travel at the speed of light, which is fast enough to circle Earth 7 times in a single second, it would still take billions of years just to cross it. That distance is so large, it's like trying to walk across the entire Earth. But the Earth keeps stretching while you walk. And yet, even something that vast might not be eternal. But why does the thought of an ending matter to us so much? Maybe it's because endings give shape to stories. Imagine reading a novel that never ends, page after page, with no final chapter. It would feel unfinished. Our minds like closure. We like arcs, beginnings, middles, ends. We see life this way too. We are born, we grow, we age, we die. It feels natural to think the universe might follow the same pattern. In fact, for most of human history, people believed the universe was fixed and unchanging. The stars were thought to be small holes in a crystal sphere. The sky was seen as solid, like a ceiling. Beyond it, perhaps heaven. It was comforting. The cosmos felt stable, eternal. But then science began to change that picture. We learned that stars are not tiny lights stuck to a dome. They are massive burning spheres, many of them far bigger than our sun. Some stars are so large that if you placed one where our sun sits, it would stretch past the orbit of Mars, wide enough to swallow the inner planets whole. That's like replacing a campfire with something as big as a city. And stars don't last forever. They are born, they shine, they die. If stars can die, what about galaxies? What about the universe itself? It's easy to think of the universe as a stage, a background where things happen. But modern science tells us something deeper. The universe is not just the stage, it is the story. Space itself can change. Time itself can change. The entire structure of reality can evolve. So if it began, could it also end? That question became even more powerful after scientists discovered that the universe had a beginning, not an endless steady state, but a starting point, a moment when everything was packed into something smaller than an atom, smaller than a grain of sand, smaller than anything we can truly imagine. When you squeeze all galaxies, all stars, all space itself into a point smaller than a speck of dust, it sounds impossible. It's like compressing every ocean on Earth into a single drop of water. And yet, that's what the evidence suggests. the universe began. So the next natural question is simple. If it had a beginning, will it have an ending? There's also something more personal here. When we think about the universe ending, we are really asking about our own place in it. If everything fades away one day, does that make our lives small? Does it make our struggles meaningless? Or does it make this moment more precious? It's interesting. We rarely think about the sun burning out, even though it will, about 5 billion years from now, which sounds like forever, but in cosmic terms is like waiting a few minutes compared to the universe's full lifespan. Our sun will swell and change. It will grow so large it could swallow Mercury and Venus, possibly even Earth. 5 billion years is hard to picture. If 1 year were the length of a single second, 5 billion years would be more than 150 years of continuous seconds ticking by, longer than any human lifetime stacked back to back. And yet, compared to the possible lifespan of the universe, even that is short. So why are we drawn to the end? Maybe because we are the only known beings who can imagine it. A cat does not worry about the heat death of the cosmos. A tree does not wonder about dark energy, but we do. We lie awake and ask, what happens when the stars go out? There's something beautiful about that. Out of all the atoms swirling in this enormous universe, some of them arranged themselves into minds capable of asking about the fate of everything. It's almost poetic, though not in a dramatic way, just quietly amazing. We are small. Yes, if Earth were the size of a coin, the observable universe would be larger than the entire continent of Asia laid flat in front of you, and that still wouldn't capture its true size. But small does not mean unimportant. The universe may be vast beyond understanding, but it is only through minds like ours that it becomes aware of itself. And so we ask, will it freeze? Will it tear itself apart? Will it collapse and begin again? For thousands of years, these were myths. Today, they are scientific questions, and the answers are more surprising, and in some ways more peaceful than the ancient stories ever imagined. As we gently move forward, we'll begin to explore what the universe is actually doing right now, because to understand how it might end, we first need to understand something simple but astonishing. The universe is not sitting still, it is changing. Even as you lie here listening, space itself is stretching, and that quiet stretching may hold the key to how everything eventually comes to an end. As we move forward, feel free to share where you're listening from, or leave a quick thought below. And if this channel means something to you, subscribing is a small way to support the journey. For a long time, people believed the universe was still, not calm in the sense of peaceful, but still, like a painting hanging on a wall. The stars seemed fixed. The constellations held their shapes year after year. The sky looked the same to your great-grandparents as it does to you. It felt solid, permanent. But in the early 1900s, that picture began to change. At that time, many scientists believed our galaxy, the Milky Way, was the entire universe, a single island of stars, surrounded by endless darkness. Imagine standing on a beach, thinking your island is the only land in existence. That was the mindset. Then astronomers began noticing faint, cloudy patches in the sky. Were they small gas clouds inside our galaxy, or something else? This question led to one of the biggest discoveries in human history. An astronomer named Edwin Hubble began carefully studying these faint patches using powerful telescopes. One of them was the Mount Wilson Observatory in California, home to one of the largest telescopes of its time. Through that telescope, Hubble saw something astonishing. Those faint smudges were not clouds inside our galaxy. They were entire galaxies of their own, each one containing billions of stars. To picture that, imagine discovering that every distant ship on the horizon is not a boat, but an entire city floating on the ocean. And there are not just a few, there are thousands, then millions, Suddenly, the universe became far larger than anyone had imagined. But Hubble didn't stop there. He began measuring the light coming from these galaxies. When light travels through space, it carries information about where it came from. By spreading that light out into a spectrum, like a rainbow, scientists can see tiny shifts in its color. And here's where things became even more surprising. Almost every galaxy he observed showed a shift toward red. Now you might ask, why red? When something moves away from us, its light stretches slightly, shifting toward the red end of the spectrum. It's similar to how the sound of a passing ambulance changes pitch. As it approaches, the sound waves are compressed, and the pitch is higher. As it moves away, the sound stretches out and becomes lower. Light behaves in a similar way, so when Hubble saw that nearly all galaxies were redshifted, it meant they were moving away from us. Not a few, not some, almost all of them. And the farther away a galaxy was, the faster it appeared to be moving away. This was not random motion. It was a pattern. Imagine drawing dots on the surface of a balloon. Then, you slowly inflate it. As the balloon grows, every dot moves away from every other dot. Not because the dots are crawling across the surface, but because the surface itself is stretching. That was the realization. The universe is expanding. Space itself is growing. It's important to pause here and ask something that naturally comes to mind. If everything is moving away from us, does that mean we are at the center of the universe? It feels that way, doesn't it? But the answer is no. If you were standing on any other galaxy, you would see the same thing. Everything would appear to be moving away from you too, just like any dot on the balloon sees all the other dots moving away as the balloon inflates. There is no special center in space. The expansion happens everywhere at once. To grasp how big this is, consider this. Some galaxies are moving away from us at thousands of kilometers per second. That's fast enough to travel from one side of the United States to the other in just a couple of seconds. And the most distant galaxies we can observe are moving away so quickly that their light has been traveling toward us for over 13 billion years, longer than human language has existed, by an unimaginable margin. In fact, if the entire history of the universe were compressed into a single calendar year, with the Big Bang at midnight on January 1st, human civilization would appear only in the last few seconds before midnight on December 31st. We are very late arrivals, and yet here we are, discovering that the universe is not static. It is dynamic, alive with motion. You might wonder, what does this expansion mean for the future? If galaxies are moving away from each other now, will they keep doing that forever? Will space continue stretching without limit? Or could something slow it down? When Hubble made his discovery in the 1920s, it completely changed the conversation. Before that, scientists debated whether the universe was eternal and unchanging. Afterward, it became clear that the universe had a history. If it is expanding now, that means it must have been smaller in the past, like rewinding a balloon back to the moment before it was inflated. And that idea led directly to the concept of the Big Bang, the beginning of cosmic expansion. But for our question tonight, will the universe ever end? The expansion is the key, because the way something ends often depends on how it moves. Think of throwing a ball into the air. If you throw it gently, gravity pulls it back down. If you throw it hard enough, it might escape your hand for good. So which is the universe doing? Is it expanding slowly enough that gravity might eventually pull everything back together? Or is it expanding fast enough to keep going forever? For much of the 20th century, scientists believed gravity would eventually slow the expansion. After all, gravity pulls everything with mass toward everything else. Every star, every galaxy, every cloud of gas is tugging on every other object in the universe. It seemed reasonable to think that over billions of years, that pulling might bring the expansion to a halt. But the universe had another surprise waiting, because as astronomers continued measuring distant galaxies, they began to notice something even stranger. The expansion wasn't slowing down, it appeared to be speeding up. And that discovery would change our understanding of cosmic fate once again. But for now, simply sit with this thought. The universe is not frozen in place. It is stretching in every direction, like a vast invisible fabric, slowly being pulled outward. Even in the quiet of this moment, space itself is growing, and whatever ending awaits the cosmos will be shaped by that silent, steady expansion. When we hear that the universe is expanding, it's easy to picture galaxies flying outward into empty space, almost like fireworks exploding in slow motion. But that picture isn't quite right. It feels natural to imagine a giant blast long ago, with galaxies shooting through darkness like sparks from a campfire. So you might quietly wonder, if everything is moving outward, what are they moving into? Is there empty space outside the universe? Is there some kind of edge? The gentle answer is this: the expansion is not galaxies moving through space. It is space itself stretching. That can be hard to picture at first. Let's slow it down. Imagine you draw small dots on the surface of a balloon. Each dot represents a galaxy. Now, as you inflate the balloon, the dots move away from each other, not because they are crawling across the rubber. They are staying in place. The surface itself is expanding. That's the key idea. In our universe, galaxies are mostly staying where they are. It's the space between them that is growing. But even the balloon image has limits, because a balloon expands into the air around it. Our universe doesn't expand into anything. There is no outside space it grows into. The expansion is happening within itself. So where is it expanding? Everywhere. If you're lying still right now, the space between you and a distant galaxy is getting slightly larger every second. Not in a way you can feel, not in a way that changes your room. Gravity and other forces hold small things together very tightly. Your body, your house, even our entire galaxy is not being stretched apart by expansion. But on very large scales, across millions and billions of light years, the stretching becomes noticeable. To give you a sense of scale, a light year is the distance light travels in 1 year. Light moves incredibly fast enough to circle Earth 7 times in a single second. In 1 year, it travels about 9.5 trillion kilometers. That's like going around the Earth's equator more than 200 million times. When we talk about galaxies being millions of light years apart, we are talking about distances so vast that even light, the fastest thing in existence, takes millions of years to cross them. And those distances are slowly increasing. Now you might ask, if space is stretching everywhere, why aren't we expanding too? It's a good question. The reason is that expansion is very weak on small scales. Gravity, electromagnetism, and the forces inside atoms are far stronger locally. Think of it like drawing tiny dots on a stretchy rubber sheet, but then gluing some of them together with strong glue. As you stretch the sheet, the glued dots stay together. Galaxies are like those glued clusters. Inside a galaxy, gravity is strong enough to hold stars in orbit. Inside a solar system, gravity keeps planets circling their star. Inside atoms, electric forces bind particles tightly together. So while space expands between galaxies, it does not pull apart stars, or people, or planets. This leads to another natural thought. If everything is moving away from everything else, does that mean we are drifting apart from nearby galaxies too? Yes, but only if they are far enough away. Our nearest large neighbor, the Andromeda Galaxy, is actually moving toward us, not away. It's about 2.5 million light-years away, which sounds huge, but in cosmic terms is relatively close. That distance is like living 2 towns over instead of across an ocean. Gravity between our galaxy and Andromeda is stronger than the pull of expansion at that distance. So in about 4 to 5 billion years, roughly the same time the Sun begins its final transformation, the two galaxies will slowly merge. But beyond our local group of galaxies, expansion wins. The farther a galaxy is, the faster it appears to recede. It's not because those galaxies are racing through space at crazy speeds. It's because there is more expanding space between us and them. If 1 million kilometers of space expands by a tiny fraction, that's small. But if 1 billion light-years of space expands by that same tiny fraction, the total increase becomes enormous. It's like stretching a rubber band by just 1%. If the band is only 1 centimeter long, the change is tiny. But if the band is 1 kilometer long, 1% becomes 10 meters. About the length of a city bus. Scale changes everything. So the expansion of the universe is not an explosion from a center. It is not galaxies rushing through emptiness. It is the steady growth of the fabric of space itself. Even now, as you rest, space between distant galaxies is growing by thousands of kilometers each second. Not because they are pushing away, but because the cosmic fabric beneath them is stretching. And this raises a quiet, important thought. If space can stretch, can it stretch forever? Will it slow down? Will it stop? Or could it stretch faster and faster? At first, many scientists assumed gravity would eventually slow this expansion. After all, gravity is everywhere. Every piece of matter pulls on every other piece. It seemed reasonable to think that over enough time, gravity might act like a brake. Imagine tossing a ball upward. It rises, slows, stops, and falls back down. The pull of gravity always wins in the end. Would the universe do the same? Would expansion slow, pause, and then reverse? For much of the 20th century, that was the big question. Astronomers tried to measure how fast expansion was happening, and whether it was gradually slowing. The fate of everything, stars, galaxies, time itself, seemed to hang on that answer. And then, toward the end of the 90s, new measurements brought a shock. Instead of slowing down, the expansion appeared to be speeding up. It was as if the ball thrown into the air suddenly accelerated upward, instead of falling back. Something unexpected was at work, something pushing space apart. And whatever that force is may determine how this entire story ends. For many decades, scientists believed they were watching a slow cosmic tug-of-war. On one side was expansion, the stretching of space itself, carrying galaxies farther apart. On the other side was gravity, the quiet, steady pull that draws matter together. Gravity is familiar. You feel it every day. It keeps your feet on the ground. It holds the moon in orbit around Earth. It keeps Earth circling the sun at about 30 kilometers per second, fast enough to travel from one side of a large country to the other in just a couple of minutes. Gravity feels dependable, predictable. So it made sense to imagine that, given enough time, gravity might slow the expansion of the universe. Picture throwing a ball straight up into the sky. If you toss it gently, it rises a little, slows down, then falls back into your hand. If you throw it harder, it rises higher, but gravity still pulls it back. If you could somehow throw it fast enough to escape Earth completely, it would never return. Scientists wondered, which case describes the universe? Was the expansion like a gentle toss, destined to fall back inward? Or was it fast enough to escape forever? To answer that, they needed to measure two things. First, how fast is the universe expanding right now? Second, how much matter is out there creating gravitational pull? Because gravity depends on mass. The more mass there is, the stronger the pull. Imagine placing two bowling balls close together. They attract each other slightly. You don't notice it, because the force is tiny. But if those bowling balls were the size of planets, the pull would be powerful enough to shape orbits. Now imagine not just two objects, but billions upon billions of galaxies, Each galaxy contains billions of stars, and many of those stars are much larger than our Sun, some wide enough to stretch past the orbit of Jupiter, which is 5 times farther from the Sun than Earth is. All that mass creates gravity, and gravity doesn't turn off at long distances. It weakens, yes, but it never truly disappears. So the question became, is there enough mass in the universe to eventually stop expansion? For much of the 20th century, scientists believed there might be. They imagined 3 possible futures. In the first case, if there was a lot of mass, gravity would eventually overpower expansion. The universe would slow, stop, and reverse. Galaxies would begin drifting back toward one another. Over billions and billions of years, everything would collapse into a hot, dense state again, like rewinding the cosmic clock. In the second case, if there was just the right amount of mass, expansion would slow down forever, but never quite stop. It would stretch outward more and more slowly, like a car running out of fuel, but never fully coming to rest. In the third case, if there wasn't enough mass, gravity would be too weak to halt expansion. The universe would keep expanding forever. At first glance, this might seem like a simple calculation. Just count the matter. But counting all the matter in the universe is not easy. Much of it is invisible. When astronomers looked at galaxies, they noticed something strange. The outer edges of galaxies were rotating too fast. Based on the visible stars alone, those outer stars should have drifted away, like sparks flying off a spinning wheel. But they didn't. Something unseen was holding them in place. It was as if you saw leaves circling rapidly around a tree, yet the branches weren't thick enough to support them. There had to be hidden structure. This led to the idea of dark matter, invisible mass that does not shine or reflect light, but still has gravity. And dark matter is not rare. In fact, it appears to make up far more mass than all the visible stars and planets combined. If you gathered all the visible matter in the universe, every star, every planet, every cloud of gas, it would be only a small fraction of the total mass inferred from gravity. So now, the calculation changed. Scientists had to include not only visible matter, but dark matter as well. For years, teams of astronomers measured distant galaxies, studying how fast they were moving away and how much mass might be pulling them back. It felt like watching a slow-motion race, expansion pulling outward, gravity pulling inward. Which would win? By the 1980s and early 1990s, many researchers believed gravity would at least slow the expansion significantly. The debate centered on how much it would slow, not whether it would. After all, gravity had shaped everything we could see. It formed stars. It built galaxies. It sculpted clusters containing thousands of galaxies bound together across distances of millions of light years. Wide enough that if you could drive across one at highway speed without stopping, it would take far longer than human civilization has existed. Gravity seemed powerful and patient. It had billions of years to work. But then new observations began to hint at something unexpected. When astronomers looked at extremely distant exploding stars, special types that shine with known brightness, they could measure how fast the universe was expanding in the past. It was like looking at old photographs of a growing child to see how their height changed over time. And what they found did not match expectations. The expansion was not slowing down as much as gravity predicted. In fact, it appeared to be speeding up. At first, many scientists thought there must be a mistake. Perhaps the measurements were wrong. Perhaps the stars were not behaving as expected. But as more data came in, from different teams and different telescopes, the result remained the same. The tug-of-war was not balanced the way we thought. Gravity was not winning. Something else was quietly pushing space apart. Something stronger, on the largest scales than gravity itself. And that discovery would change the story of the universe's ending. in a way no one had predicted. In the late 1990s, a quiet revolution took place in astronomy. It didn't happen with a loud explosion or a dramatic announcement at first. It happened slowly, through careful measurements, late nights at observatories, and teams of scientists double-checking their data again and again. They were studying distant exploding stars called supernovae. These were not ordinary stars gently fading away. These were powerful explosions, brief flashes so bright they can outshine entire galaxies for a short time. For a few weeks, one dying star can shine brighter than billions of stars combined. To picture that, imagine a single streetlight suddenly glowing brighter than every light in an entire city. That's the scale we're talking about. These particular supernovae were special because they exploded in a very consistent way. They reached nearly the same peak brightness each time. That made them useful as standard candles. If you know how bright something truly is, and you see how dim it appears from Earth, you can calculate how far away it must be. It's like seeing a 100-watt light bulb across a field. If it looks faint, you know it's far away. If it looks bright, it's closer. Two major research teams set out to measure these distant supernovae. One was called the Supernova Cosmology Project, led by Saul Perlmutter. The other was the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees. Their goal was simple: measure how fast the universe was expanding in the past. If gravity was slowing expansion, then distant supernovae, whose light has been traveling for billions of years, should show evidence of that slowing. Think of watching a car roll uphill. If it's losing speed, you can tell by comparing where it was earlier to where it is now. The scientists expected to see that the universe used to expand faster and was gradually slowing down, but when they analyzed the data, something didn't add up. The distant supernovae were dimmer than expected. Dimmer means farther away. Farther away means the universe expanded more than predicted, while their light was traveling toward us. In other words, instead of slowing down, the expansion had been speeding up. At first, the teams were cautious. Was there dust in space dimming the light? Were the supernovae different in the distant past? Were there errors in the instruments? They checked everything. They compared results. They repeated observations. And slowly, the same answer kept appearing. The universe is not just expanding, it is accelerating. Imagine throwing a ball upward and seeing it move faster and faster the higher it climbs, as if something invisible were pushing it from below. That would feel strange. It would break your expectations. That's exactly how this discovery felt. Gravity pulls inward. It slows things down. So what could be pushing outward strongly enough to overcome gravity across the entire universe? The answer was something no one fully understood: a new form of energy. They called it dark energy, not because it was evil or mysterious in a dramatic way, simply because it was unknown, invisible, not directly detectable. Just as dark matter revealed itself through gravity, dark energy revealed itself through expansion. To give you a sense of scale, this acceleration is subtle on small distances. You won't notice space stretching in your room. You won't see your bookshelf drift away. But across billions of light years, the effect is enormous. Some galaxies are now moving away from us, so fast that their light will never reach us again. The expansion of space between us and them is increasing so quickly that even light, which travels fast enough to circle Earth 7 times in a single second, cannot close the gap. It's like trying to swim toward a shoreline that is drifting away faster than you can paddle. The discovery was so important that in 2011, Saul Perlmutter, Brian Schmidt, and Adam Rees were awarded the Nobel Prize in Physics. But beyond awards and recognition, the deeper impact was this: the fate of the universe changed overnight. Before this discovery, many believed gravity might one day pull everything back together in a grand collapse. A dramatic ending, perhaps, followed by a new beginning. But accelerating expansion suggested something else entirely. If expansion keeps speeding up, galaxies will drift farther apart, over trillions of years. That's thousands of billions of years, far longer than the time since dinosaurs walked the Earth. The universe could become colder, darker, and emptier, not with a bang, but with a fading. This was not the fiery ending of ancient myths. It was something quieter, a slow stretching, a thinning of energy, a gradual dimming of stars. And naturally, this raises a gentle question. What exactly is dark energy? Is it a property of space itself? Is it some unknown field filling the cosmos? Has it always been there, or did it change over time? Scientists are still trying to understand it. What we do know is this: dark energy appears to make up about 70% of the total energy content of the universe. That means everything you can see, stars, planets, galaxies, makes up only a small fraction of what exists. If the universe were a pie sliced into 10 pieces, about 7 slices would be dark energy, 2 slices would be dark matter, and less than 1 slice would be all the visible matter combined. We are living inside a cosmos dominated by something we barely understand, and that mysterious energy is shaping the future. As space continues to expand faster and faster, the ending of the universe may not be a sudden collapse or explosion. It may be a long, slow drifting apart, a quiet stretching into darkness. But to understand that future, we need to look more closely at this strange force, this dark energy, and ask what it might really be. So what is this quiet force that seems to be pushing the universe apart? Dark energy. The name sounds mysterious, but it really just means we don't fully understand it yet. It doesn't glow, it doesn't cast shadows, it doesn't clump together like matter. We can't hold it, see it, or detect it directly with instruments the way we detect light or particles. And yet its effects are written across the entire cosmos. When astronomers measure distant galaxies and see that expansion is speeding up, dark energy is the simplest explanation. It behaves like a kind of pressure built into space itself, a gentle but persistent push outward. You might wonder, how can empty space have energy? That's a natural question. We tend to think of empty space as nothing, just a gap between things. But modern physics tells us that even empty space is not truly empty. On the smallest scales, far smaller than atoms, space is alive with tiny fluctuations. Particles briefly appear and disappear, like bubbles forming and popping in boiling water. If you zoomed in far enough, the vacuum would not look calm, it would look restless. Some scientists think dark energy could be related to this vacuum energy. In simple terms, space itself may contain a small amount of built-in energy, and when space expands, more space exists, which means more of this energy appears. It sounds strange at first, but think of it this way. Imagine every square meter of space contains a tiny, tiny amount of energy, so small that in a room the size of your bedroom, it would be less energy than a single falling leaf. Almost nothing. But now imagine the entire universe. The observable universe is about 93 billion light years across. That's so wide that if you tried to drive across it at highway speed without stopping, it would take far longer than the age of the universe itself. The distance is beyond everyday intuition. When you multiply even a tiny amount of energy by a volume that large, it adds up. And that accumulated energy could be enough to push the universe apart. This idea connects to something called the cosmological constant, a term that first appeared in the equations of Albert Einstein. Einstein originally added this constant to his equations because he believed the universe was static. He needed a mathematical term to balance gravity and prevent collapse. Later, when expansion was discovered, he reportedly called it his biggest mistake. But now, many scientists think he may have accidentally been right, though not in the way he expected. The cosmological constant can be thought of as energy built into space itself, a steady, unchanging energy that does not weaken as the universe expands. If that's true, then as space grows, the total amount of dark energy increases too, because there is simply more space containing it. And that would naturally lead to accelerating expansion. But there's another possibility. Some scientists suggest dark energy might not be constant. It could be a changing field, something more dynamic. Imagine a gentle ocean tide that slowly rises over billions of years. If dark energy grows stronger over time, expansion could accelerate more and more. This possibility leads to very different futures for the universe. But before we drift too far ahead, it's important to pause and ask something simple. How strong is dark energy? Surprisingly, it's incredibly weak. If you could gather all the dark energy inside a coffee cup-sized volume of space, it would weigh far less than a single grain of sand. Its density is unbelievably small, smaller than almost anything we deal with in daily life. And yet, over the vast scale of the universe, it dominates. This is one of those ideas that feels almost backwards. Something incredibly weak, spread across unimaginable distances, becomes the most powerful force shaping cosmic destiny. It's like a whisper that fills a stadium, individually quiet, but collectively overwhelming. There's still much we don't know. Is dark energy truly constant? Will it remain steady forever? Could it fade? Could it grow stronger? Current measurements suggest it behaves very much like a cosmological constant, steady and unchanging. But our measurements, while precise, are still limited. We can only observe part of the universe, the region whose light has had time to reach us since the beginning. Beyond that horizon lies more space we cannot see. So we are trying to understand the fate of everything, using information from a portion of the whole. It's a bit like trying to predict the future of an entire ocean by studying a single bay. Still, the evidence so far points in one direction. If dark energy remains constant, the universe will continue expanding faster and faster. Galaxies will drift apart. Over trillions of years, the sky will grow emptier. Stars will burn out. Matter will grow thin and cold. This possible ending is sometimes called the Big Freeze, not because everything instantly turns to ice, but because energy becomes evenly spread out. Temperatures drop. Activity slows. Imagine a campfire slowly fading through the night. At first, bright flames leap upward. Later, only glowing embers remain. Eventually, even the embers cool to grey ash. The universe may follow a similar path, though on a timescale so vast it makes human history look like a blink. And here is a gentle thought. Right now we are living in a special era. Stars are shining, galaxies are visible, the night sky is rich with light. We exist in a time when the universe is active and full of structure. Dark energy may one day lead to a very different scene. But for now, the cosmic story continues. Shaped by a force we are only beginning to understand. And as we explore further, we will see how this steady acceleration may lead to a future that is quiet, cold, and unimaginably long. If dark energy continues to push the universe apart, gently but steadily, then the most likely ending is not a dramatic collapse or a violent explosion. It is something quieter, a slow fading. This idea is often called the heat death of the universe. Sometimes it's also called the Big Freeze, not because everything suddenly turns to ice, but because over immense stretches of time, the universe becomes colder, darker, and more still. To understand this, imagine a hot cup of coffee sitting on a table. At first, it's warm. Steam rises. Heat flows into the air. After a while, it cools. Eventually, it reaches the same temperature as the room. The energy spreads out evenly. Nothing dramatic happens. It simply settles. The universe behaves in a similar way. Right now, the cosmos is full of energy differences. Stars are hot, millions of degrees at their cores, which is hotter than the center of a blast furnace by a wide margin. Planets are cooler. Space in between is colder still. Energy flows from hot places to cold places, and that flow creates activity. Stars shine because nuclear reactions in their cores release energy. Our sun, for example, produces more energy every second than humanity has used in all of recorded history combined, and it has been doing that for about 4.6 billion years, which is like running a power plant continuously since before complex life existed on Earth. But stars don't shine forever, they burn fuel, and fuel runs out. In the heat death scenario, the universe continues expanding. Galaxies drift farther apart over time, trillions of years, which is thousands of billions of years. Stars slowly exhaust the hydrogen in their cores. New stars will continue forming for a long time, especially from clouds of gas pulled together by gravity. But eventually, even those gas clouds will be used up. You might wonder, how long will that take? Current estimates suggest that active star formation could continue for perhaps 100 trillion years. That's 100,000 billion years. To compare, the universe right now is about 13.8 billion years old, so we are still in the early chapters, like being on page 14 of a book that might stretch for 100,000 pages. But even that long era will pass. Once the gas needed to form new stars is gone, the universe will slowly grow dimmer. Existing stars will age and die. Some will swell into red giants, growing so large they could engulf nearby planets. Others will explode as supernovae, scattering heavy elements into space. After that, what remains are stellar remnants, white dwarfs, neutron stars, and black holes. Over even longer timescales, galaxies themselves will change. As space continues expanding faster and faster, distant galaxies will slip beyond our cosmic horizon. Light from them will no longer reach us. It's like watching ships on the ocean drift beyond the curve of the Earth, one by one, until only your own small island remains visible. In the far future, observers inside a galaxy may see nothing but their own cluster of stars. Everything else will have moved too far away. But the cooling continues. The temperature of the universe is already very low. The average temperature of space today is about 2.7 degrees above absolute zero, which is about minus 270 degrees Celsius, colder than any winter night on Earth, by an unimaginable margin. That faint warmth is leftover radiation from the early universe. As expansion continues, that temperature will drop even further. Eventually, stars will no longer shine. White dwarfs, the small, dense cores left behind by sun-like stars, will slowly cool over trillions of years. Imagine a glowing ember from a fire, fading from bright orange to deep red, then to black. That's what will happen to most stellar remnants. Neutron stars and black holes will remain, but they too will exist in a universe growing emptier and colder. Energy will be spread thin. In physics, this idea connects to something called equilibrium, when energy is evenly distributed and no more work can be done, when there are no differences in temperature, no gradients, no flows. Think again of that cup of coffee. Once it has cooled to room temperature, you can't extract useful heat from it anymore. It's just stable. In the far future, the universe may reach a similar state, not frozen solid like a block of ice, but quiet. No new stars, no bright galaxies, just faint remnants drifting through ever-expanding darkness. It might sound lonely, but remember, this unfolds over timescales so vast, they almost lose meaning. If the current age of the universe was shrunk to 1 hour, the era of active star formation would stretch far beyond an entire day. We are living in a bright era. The night sky today is rich with light. Billions of galaxies are visible with powerful telescopes. Cosmic activity is everywhere. The heat death scenario suggests that this brightness is temporary, not because something goes wrong, but because energy spreads out, just as every fire eventually fades when fuel runs low. And yet, even in this slow fading, there is something gentle about it. The universe does not end in chaos. It doesn't shatter or scream. It simply expands, cools, and grows quiet. But why does it move in that direction at all? Why does energy spread out instead of gathering back together? To answer that, we need to understand a deeper rule of nature, one that governs not just the universe, but your kitchen, your body, and every physical process around you. A rule that quietly pushes everything toward disorder. A rule called entropy. To understand why the universe might slowly fade into darkness, we need to talk about a quiet rule that shapes everything. It's called entropy. The word may sound technical, but the idea is simple. Entropy is a measure of disorder, and there is a rule known as the second law of thermodynamics that says entropy always increases over time in a closed system. That may sound abstract at first, so let's bring it down to something familiar. Imagine you clean your room perfectly. Everything is neatly arranged, clothes folded, books stacked, desk clear. Then you live in it for a week. Without constant effort, things slowly become messy again. Clothes pile up, papers scatter, dust gathers, order naturally drifts toward disorder. You can fight it by cleaning, but that requires energy. If you stop putting in effort, the mess grows. The universe behaves in a similar way. At the beginning, during the Big Bang, the universe was incredibly hot and dense. Energy was concentrated. Matter was tightly packed. As the universe expanded, energy spread out, temperatures dropped, structure began to form. Stars, galaxies, planets. But overall, on the largest scale, energy has been spreading thinner and thinner. Entropy increases. Now you might ask, if entropy means disorder increases, how do stars and galaxies form at all? Aren't they examples of order? It's a good question. Locally, gravity can create structure. It pulls matter together into stars and galaxies. That seems like increasing order. But in the process of forming those structures, energy is released. Heat radiates outward into space. That radiation spreads out and increases the total entropy of the universe. So even when order appears in one place, disorder increases overall. It's like building a snowman. You create a neat shape out of snow, but your movements generate heat, and eventually the snowman melts. On balance, disorder wins. Entropy is not about chaos in a dramatic sense. It's about energy becoming evenly distributed. Think again about that hot cup of coffee. At first, the heat is concentrated in the liquid. The surrounding air is cooler. That temperature difference allows energy to flow. But over time, the coffee cools and the air warms slightly. The difference disappears. When everything reaches the same temperature, no more heat flows. No more useful work can be done. That's what heat death means on a cosmic scale. In the far future, energy will be spread so evenly across space that there will be no gradients left, no hot stars radiating into cold space, no temperature differences driving processes. The universe will not be frozen in a solid sense. It will simply be at near perfect balance. And balance, in this case, means stillness. Right now, the universe is far from that state. Stars burn at millions of degrees. Space between galaxies is just a few degrees above absolute zero, about -270 degrees Celsius, colder than the coldest natural place on Earth by hundreds of degrees. That difference fuels activity. But as stars burn out and galaxies drift apart, those temperature differences shrink. Entropy increases. Another way to picture entropy is with a deck of cards. A brand new deck comes in perfect order. All the hearts together, then diamonds, and so on. Shuffle it once, and the order changes. Shuffle it many times, and the cards become randomly mixed. There are far more ways for a deck to be mixed than perfectly arranged. In the same way, there are far more ways for the universe to be disordered than ordered. So over time, it moves toward the more probable state, disorder. And this is not just about rooms, or coffee, or cards. It applies to everything physical. It applies to stars burning fuel. It applies to chemical reactions. It applies to life itself. Life feeds on energy differences. We eat food which stores chemical energy. Our bodies use that energy to maintain order, to keep cells structured, to keep hearts beating. But if energy stops flowing, life cannot continue. That's why the eventual leveling out of energy in the universe matters so much. You might wonder, does entropy mean the universe is running down like a battery? In a way, yes. Imagine a battery powering a flashlight. At first, the light shines brightly. Over time, the energy inside the battery spreads out as heat and light. Eventually, the battery is drained. The flashlight grows dim, then dark. The universe may be like a cosmic battery, slowly discharging over unimaginable timescales. But here's something fascinating. The increase of entropy also gives us a sense of time. Why does time seem to move forward? Because entropy increases. You never see a broken glass spontaneously reassemble itself. That would decrease entropy. Instead, glasses fall and shatter. Ice melts in warm air. Smoke spreads through a room but never gathers itself back into the corner. Entropy gives time its direction. So when we talk about the end of the universe as a heat death, we are really talking about the final stage of this process. Energy spread out, differences erased, motion fading. Imagine a vast ocean at sunset. At first, waves move, wind blows, currents swirl. Slowly the wind calms, the surface smooths, the water becomes still. Now stretch that image across trillions upon trillions of years. That is the path entropy suggests. It's not violent, it's gradual. But before we reach that ultimate quiet, many dramatic events will unfold, especially in the lives of stars, because stars are the engines of structure, and their endings will shape the long fading chapters of the cosmos. Right now, the universe is full of light. Look up at the night sky and you see stars shining like steady points of white and gold. Some are small, some are enormous, some are so far away that their light began its journey before humans built the first cities. But every one of those stars has something in common. They are temporary. A star is not a permanent object. It is more like a fire, a giant controlled burn held together by gravity. Take our sun as an example. The sun is about 1.4 million kilometers wide. That's wide enough to fit more than 100 Earths, side by side across its face. And inside its core, temperatures reach around 15 million degrees Celsius, hotter than anything we can create on Earth by an enormous margin. So what keeps it shining? At its center, hydrogen atoms are being squeezed together by gravity so tightly that they fuse into helium. This process releases energy, huge amounts of it. That energy pushes outward, balancing the inward pull of gravity. It's like a constant tug of war inside the star. Gravity tries to crush it. Fusion pushes back. As long as that balance holds, the star shines steadily. But hydrogen fuel is not infinite. Our sun has enough fuel to shine for about 10 billion years in total. It is currently about 4.6 billion years old, almost halfway through its main life. If a star's life were a human lifespan of 80 years, our sun would be around 40 years old, calm, stable, middle-aged. Eventually, though, the hydrogen in the core will run low. So what happens then? Without enough fuel, fusion slows. The outward pressure weakens, gravity begins to win. The core contracts, growing hotter and denser. That extra heat ignites new fusion reactions in layers around the core. The outer layers of the sun will expand dramatically. It will become a red giant. When that happens, about 5 billion years from now, the sun could swell large enough to reach the current orbit of Mercury, possibly even Venus. Imagine the sun growing so wide it would swallow the inner planets entirely. That expansion would be like taking a basketball and inflating it until it fills an entire room. Earth's fate is uncertain. It may be engulfed, or it may survive but become a scorched, lifeless world. After this giant phase, the sun will shed its outer layers into space. What remains will be a dense core called a white dwarf. A white dwarf is about the size of Earth, roughly 12,000 kilometers across, but it contains about half the mass of the sun. That means its material is incredibly dense. A teaspoon of white dwarf material would weigh as much as a large mountain, and yet it will no longer produce energy. It will slowly cool over trillions of years, fading from white to red to black. This is the quiet ending of a sun-like star. But not all stars are like our sun. Some are far more massive, 8 times heavier, 10 times heavier, even more. These giants burn through their fuel much faster. A massive star may live only a few million years. Compared to the sun's 10 billion year life, that's like living for just a few days instead of decades. Why so short? Because bigger stars burn hotter and faster. Imagine 2 candles, one small and steady, the other thick and blazing. The blazing candle burns out much sooner. When a massive star runs out of fuel, its ending is far more dramatic. The core collapses suddenly under gravity. In a fraction of a second, less time than it takes to blink, the core shrinks dramatically. The outer layers crash inward and then rebound outward in a titanic explosion called a supernova. For a brief moment, the exploding star can shine brighter than an entire galaxy. The explosion releases more energy in seconds than our sun will produce in its entire lifetime. Afterward, what remains depends on the mass. Some cores become neutron stars, objects about 20 kilometers wide, roughly the size of a small city, but containing more mass than our sun. That means they are unbelievably dense. A teaspoon of neutron star material would weigh as much as a mountain range. If the original star was even more massive, the collapse continues. Gravity becomes so strong that not even light can escape. A black hole is born. So across the universe, stars are constantly being born, living and dying. Massive stars die quickly and violently. Smaller stars live longer and fade gently, but no star lasts forever. And here's the important part for the future of the universe. Stars are the main sources of light and energy that shape cosmic structure. They create heavy elements, they power planets, they make life possible. Without stars, the universe becomes darker. Right now, star formation is still happening. Clouds of gas collapse under gravity to form new suns. But over time, that gas supply is being used up. Each generation of stars consumes hydrogen. Some of it gets locked away in stellar remnants. Some is scattered, but not all of it can be reused. Slowly, over trillions of years, the raw material for new stars will run thin. The sky will change. Instead of bright young stars forming, there will be more white dwarfs, more neutron stars, more black holes. The bright, active era of star birth will end. And when no new stars form, the universe will enter a quieter chapter. A chapter where the lights slowly go out, one by one. But that fading is still far in the future. For now, stars still burn. The cosmos still glows. Yet even tonight, somewhere in the vast darkness, a star is reaching the end of its fuel, and the universe moves one small step closer to its long, quiet cooling. Right now, somewhere in the universe, a new star is being born. Inside a cold, dark cloud of gas, gravity is quietly pulling hydrogen atoms closer together. The cloud slowly contracts. As it shrinks, it heats up. Over time, sometimes millions of years, the center becomes hot and dense enough for nuclear fusion to begin. A new light turns on. This process has been happening for billions of years. Our own sun was born this way, about 4.6 billion years ago, from a collapsing cloud of gas and dust. If you could rewind time and watch it happen, you would see a faint mist slowly gathering into a bright sphere. It would be like watching fog condense into a glowing fireball over an enormous stretch of time. But this process cannot continue forever. Stars require fuel, mainly hydrogen gas. And while the universe began with vast amounts of hydrogen, that supply is not endless. Every time a star forms, it locks some of that hydrogen away. During its life, it fuses hydrogen into helium and heavier elements. When it dies, some material is returned to space, but not all of it remains usable for future star formation. Some becomes locked inside white dwarfs. Some becomes trapped in neutron stars or black holes. These remnants do not easily give their material back. Over time, more and more of the universe's gas becomes tied up in stellar remnants, and the supply of free-floating hydrogen clouds shrinks. So you might wonder, how long will star formation last? Current estimates suggest that active star formation may continue for about 100 trillion years. That's 100,000 billion years. Compared to the universe's current age of about 13.8 billion years, we are still very early. If the universe were the length of a 24-hour day, we would be only a few minutes past midnight. But even 100 trillion years is not forever. Eventually, most of the easily accessible hydrogen will be used up. The remaining gas will be too thinly spread to collapse into new stars. And when that happens, something profound occurs. No new lights will turn on. Imagine a city where no new buildings are ever constructed. Over time, old buildings crumble. Some are repaired, others fall into ruin. But without new construction, the city slowly ages. The universe will follow a similar path. Existing stars will continue shining for a long time. Small red dwarf stars, the most common type of star, can burn for trillions of years. They are small and efficient, like tiny candles that sip their fuel slowly. In fact, some red dwarfs may live for up to 10 trillion years or more. That's nearly 1,000 times longer than our sun's lifespan. But once they finally exhaust their fuel, they too will fade, and without new stars forming to replace them, the overall brightness of the universe will decline. At first, the change will be subtle. Galaxies will still contain billions of stars, but gradually, the bright blue stars, the hot, massive ones, will disappear first. These stars burn fast and die young. Over time, galaxies will glow more faintly, dominated by small, dim red stars. Eventually, even those will run out. The sky, if anyone were there to see it, would grow darker. It's worth pausing here to picture what that means. Right now, if you look up from a dark place on Earth, you can see thousands of stars with the naked eye. With telescopes, we see billions of galaxies, each one filled with billions of stars. But in the far future, galaxies will not sparkle with new life. They will contain aging stars and quiet remnants. And something else will be happening at the same time. Because the universe's expansion is accelerating, distant galaxies are drifting farther and farther away. Over trillions of years, most galaxies outside our local group will slip beyond our cosmic horizon. Their light will never reach us again. It's like watching candles placed along a shoreline, slowly carried away by a rising tide until they disappear from view. So not only will star formation end, the visible universe will shrink. Future observers, if any exist, may see only their own galaxy cluster. Everything else will have faded beyond reach. As star formation slows and stops, the universe enters what some scientists call the degenerate era. This is the age dominated by stellar remnants, white dwarfs, neutron stars, and black holes. White dwarfs will slowly cool over trillions upon trillions of years. They will fade from bright white to red, then to black. These cooled remnants are sometimes called black dwarfs, though none exist yet, because the universe is not old enough. Neutron stars will remain dense and dark. Black holes will quietly sit at the centers of galaxies, but no new stars will light up the darkness. Energy differences will shrink. Entropy will continue to rise. The cosmos will grow colder and quieter. It may feel a little sad to imagine the lights going out, but remember, this process unfolds over spans of time so vast they almost lose meaning. If one human lifetime were a single second, the era of star formation would stretch longer than all of recorded human history, multiplied millions of times over. We are living in a bright, active chapter. Stars are still being born. Supernovae still scatter heavy elements. Galaxies still shine. But one day, far beyond any calendar we can imagine, the last new star will form. And after that, the universe will slowly transition into an age ruled not by bright suns, but by something darker, by the quiet gravity of black holes. As the last new stars are born and the supply of fresh hydrogen runs thin, the universe slowly enters a different kind of age. An age not of bright, blazing suns, but of shadows. When stars die, they do not simply vanish. They leave behind remnants, white dwarfs, neutron stars, and, for the most massive stars, black holes. Over trillions of years, as star formation fades, more and more matter will end up in these compact objects. Galaxies will no longer be filled with glowing clouds of gas and newborn stars. Instead, they will become graveyards of stellar remains. And among those remains, black holes will play a central role. So what exactly is a black hole? At its heart, a black hole forms when a very massive star collapses under its own gravity. When the nuclear fuel runs out, there is nothing left to push back against gravity's pull. The core compresses so tightly that it shrinks to an incredibly small size. If enough mass is packed into a small enough space, gravity becomes so strong that not even light can escape. That's why it's called black. The boundary around a black hole is called the event horizon. Once something crosses that boundary, it cannot return. To picture the size of one, imagine a black hole formed from a star about 10 times heavier than our Sun. The event horizon of that black hole might be only about 30 kilometers across, roughly the size of a large city. Yet it would contain several times the mass of the Sun, which itself is more than 300,000 times heavier than Earth. That means an enormous amount of matter, squeezed into a region no wider than a short highway drive. At the centers of most galaxies, including our own Milky Way, there are even larger black holes, called supermassive black holes. The one at the center of our galaxy has a mass about 4 million times greater than our Sun. If you could place it where the Sun currently sits, its event horizon would stretch far beyond the orbit of Mercury, though still much smaller than the orbit of Earth. In the current universe, black holes are rare compared to stars, but as time passes, that balance will change. White dwarfs and neutron stars will remain stable for immense periods of time. But over trillions of years, gravitational interactions inside galaxies will cause objects to drift. Stars and remnants will pass near each other. Some will be flung out of galaxies entirely, like pebbles kicked from a spinning wheel. Others will spiral inward toward the central black hole. Galactic centers will slowly consume surrounding matter. Imagine a quiet whirlpool in a lake. Leaves drift near it. Some are pulled in. Others float away. Over time, the whirlpool gathers more and more debris. Black holes will act in a similar way, though on scales far beyond imagination. Over time spans far longer than the current age of the universe, perhaps 10 to the power of 20 years, which is a 1 followed by 20 zeros. Most stars in galaxies may either be ejected into intergalactic space or swallowed by black holes. To compare, the universe today is about 10 to the power of 10 years old. So we are talking about a timescale 10 billion times longer than the universe has existed so far. Numbers like that are difficult to feel. If 1 year were 1 second, 10 to the power of 20 years would be more seconds than have passed since the Earth formed by an enormous margin. During this era, galaxies will slowly lose their structure. Many stars will drift into empty space, separated from others by enormous distances. Some will fall into black holes. Others will remain isolated, slowly cooling. But black holes will persist. They are incredibly stable objects, or at least they seem to be. For a long time, scientists believed black holes would last forever. Once formed, they would simply sit there, swallowing matter and growing larger. In a universe heading toward heat death, black holes seemed like the final survivors, the last complex structures remaining after stars faded away. Picture an endless dark ocean with only a few deep whirlpools remaining. As expansion continues, galaxies beyond our local region will slip away beyond the cosmic horizon. Eventually, only gravitationally bound systems will remain connected. Over trillions of years, even galaxy clusters may disperse. Stars and remnants will drift farther apart. The universe will grow emptier. Black holes will dominate the landscape, not because they are aggressive, but because they are persistent. They do not shine. They do not burn fuel. They simply exist. And yet, even black holes are not truly eternal. This is where the story takes another unexpected turn. Because in the 1970s, a brilliant physicist named Stephen Hawking proposed something extraordinary. Black holes, he suggested, are not completely black. They slowly lose energy. They slowly evaporate. The process is unbelievably slow for large black holes, slower than almost anything else in the universe. But given enough time, even these giants may disappear. So even in the era of black holes, nothing lasts forever. The universe continues its long drift toward simplicity, from bright stars to dark remnants, from galaxies full of light to scattered points of gravity. The age of black holes may stretch for unimaginable lengths of time, but it too is only a chapter. And as we move forward, we will explore how even these seemingly eternal objects slowly fade into the quiet background of an ever-expanding cosmos. For a long time, black holes were thought to be the ultimate endpoint. Once something fell in, it was gone forever. Matter, light, even information, all trapped behind the event horizon. Black holes seemed like perfect cosmic vaults, silent, eternal. But in the 1970s, something unexpected happened. A physicist named Stephen Hawking began thinking deeply about what happens near the edge of a black hole, not just in terms of gravity, but in terms of quantum physics. And what he found surprised even him. To understand this, we need to revisit an earlier idea. Empty space is not truly empty. On very tiny scales, far smaller than atoms, space is filled with quantum fluctuations. Particles briefly appear and disappear in pairs. These are called virtual particles. They pop into existence together, then quickly annihilate each other, returning to nothing. You can imagine it like tiny bubbles forming in boiling water, then collapsing almost instantly. The bubbles are real for a brief moment, but they don't last. Normally, these particle pairs appear and vanish so quickly that no lasting effect remains. But near the event horizon of a black hole, something strange can happen. If a pair of virtual particles forms right at the edge, one particle might fall into the black hole while the other escapes before they can annihilate each other. When that happens, the escaping particle becomes real. And to an outside observer, it looks as if the black hole has emitted a tiny bit of radiation. This is called Hawking radiation. It's important to pause and ask something natural. If a black hole is emitting radiation, where does that energy come from? The answer is subtle. When one particle falls into the black hole and the other escapes, the particle that falls in can effectively carry negative energy, at least in a very specific mathematical sense. This reduces the total mass of the black hole. So as radiation escapes, the black hole slowly loses mass. It slowly shrinks. Now, before we imagine black holes vanishing tomorrow, it's important to understand just how slow this process is. For a black hole with the mass of our Sun, the time required to fully evaporate through Hawking radiation is about 10 to the power of 67 years. That's a 1 followed by 67 zeros. To compare, the universe right now is about 10 to the power of 10 years old. So we are talking about a timescale that is trillions upon trillions upon trillions of times longer than the current age of the universe. If 1 year were 1 second, the current age of the universe would be a few hundred years. But 10 to the power of 67 years would be longer than the time it would take to count every grain of sand on Earth, one by one, at 1 grain per second, repeated countless times over. It's almost beyond imagination. And supermassive black holes, the kind that sit at the centers of galaxies, would take even longer. A black hole with billions of times the mass of the Sun might take 10 to the power of 100 years to fully evaporate. That's a number so large it barely fits in thought. And yet, the key idea is simple. Black holes are not eternal. They slowly radiate energy. They slowly shrink. At first, the radiation is incredibly weak. For large black holes, the temperature associated with Hawking radiation is extremely low, much colder than the coldest parts of space today. In fact, for now, black holes absorb more energy from the cosmic background radiation than they emit. The universe is still warm enough that black holes grow slightly from surrounding radiation, but as the universe expands and cools further, there will come a time when the background temperature drops below the temperature of black holes. At that point, they will begin to lose more energy than they gain, and the long evaporation will begin. As a black hole shrinks, its temperature actually increases. That's another surprising twist. The smaller it gets, the hotter it becomes. Imagine a dying ember that grows hotter as it shrinks, glowing brighter and brighter near the end, in the final moments of evaporation. After unimaginable stretches of time, a black hole may release a burst of radiation before disappearing entirely. And then, nothing remains. No event horizon, no singularity, just radiation spreading out into the vast darkness. In the era of black holes, long after stars have died and galaxies have dispersed, these objects will dominate the cosmos. But Hawking's discovery tells us that even they are temporary. Even the deepest gravitational wells eventually drain. It's a gentle reminder of something we've seen again and again in this journey. Nothing physical lasts forever. Stars fade, galaxies drift apart, black holes evaporate, entropy continues its slow rise. You might quietly wonder, what happens after the last black hole is gone? What remains in a universe where even the darkest giants have dissolved? The answer leads us into time spans so vast they stretch language to its limits. But before we go there, it's worth sitting with this thought. For decades, black holes were considered the ultimate endpoint, the final stage of cosmic evolution. And yet, even they are only temporary structures in a universe that continues to expand and thin. The story does not end with darkness swallowing everything. Instead, darkness itself slowly dissolves, and in that distant future, beyond 10 to the power of 100 years, the universe enters an era even quieter than the age of black holes, an era where almost nothing remains at all. There will come a time far beyond any calendar we could ever write, when the universe looks nothing like it does today. No bright stars, no glowing galaxies, no swirling clouds of gas. By then, star formation will have ended trillions of years earlier. White dwarfs will have cooled into dark, cold embers. Neutron stars will drift quietly through expanding space. Most matter will have either fallen into black holes or been flung into the deep emptiness between galaxies. And black holes themselves will dominate the cosmic landscape, but even they will not last forever. As we explored, black holes slowly lose mass through Hawking radiation. The process is unimaginably slow for large black holes. For a black hole with the mass of our Sun, it would take about 10 to the power of 67 years to evaporate completely. For the supermassive black holes at the centers of galaxies, some containing billions of times the mass of our Sun, the timescale stretches to around 10 to the power of 100 years. That's a 1 followed by 100 zeros. To give some sense of scale, if every second since the Big Bang were a single grain of sand, you would need far more grains than exist on all the beaches of Earth combined to count up to 10 to the power of 100 seconds. These numbers are so large that the human mind almost gives up trying to picture them. But in that distant future, the background temperature of the universe will be incredibly low, far lower than it is today. Right now, space is about 2.7 degrees above absolute zero, which is around minus 270 degrees Celsius, colder than anything naturally found on Earth. As the universe expands, that temperature continues to drop. Eventually, the cosmic background will be colder than any black hole. At that point, black holes will lose energy steadily, no longer gaining anything from their surroundings. Over spans of time that dwarf even the lifetimes of stars, they will shrink, slowly at first, then as they get smaller, more quickly. Because as a black hole loses mass, its temperature rises. A smaller black hole radiates more strongly than a larger one. It's almost like a shrinking ice cube that suddenly begins to melt faster and faster near the end. Though in this case, the process unfolds over periods so vast, they make all of human history look like a brief flicker. Imagine waiting not just billions or trillions of years, but numbers so large that writing them out would fill entire pages. And then, one day, if we can even use the word day meaningfully at that scale, the last supermassive black hole finishes evaporating. There is no explosion in the usual sense, just a final burst of radiation as the remaining mass converts into energy. And then it is gone. No event horizon, no singularity, no dark center anchoring a galaxy, just energy spreading outward into already vast, nearly empty space. So what remains after the last black hole evaporates? Very little. By that time, most matter may have already decayed. If protons are unstable, which we will explore soon, but even if some particles remain, they will be scattered across distances so enormous that interactions become incredibly rare. Imagine taking every grain of sand from every beach on Earth and spreading them evenly across the entire surface of the planet, so that each grain sits thousands of kilometers away from the next. Now imagine something even more extreme. Particles separated by distances so large that even light, traveling at 300,000 kilometers per second, fast enough to circle Earth 7 times in a second, would take trillions of years to cross the gap. Collisions would be almost non-existent. The universe would become a thin, cold mist of elementary particles and radiation. No stars to light the darkness, no black holes to bend space, just a faint background of low-energy photons and drifting particles. In this era, entropy is nearly maximized, energy is spread out almost perfectly evenly. No gradients remain, no engines run. It's hard to imagine what happening even means in such a state, because events require interactions, and interactions require proximity. When everything is separated by enormous distances, the universe becomes extremely quiet. If someone, or something, could observe this far future, the sky would be utterly black, not just dark like a rural night, not sprinkled with faint stars, but black in a deeper sense. Empty, the structure we associate with the universe. Galaxies, clusters, cosmic webs stretching across hundreds of millions of light years will be gone. The cosmic web today spans distances so large that light takes millions of years to travel between its filaments. It's like a three-dimensional spiderweb stretching across space, with galaxies sitting along its strands. But in the far future, even that structure dissolves. Expansion continues. Distances grow, particles drift farther apart. The last black hole's evaporation marks the end of what we might call the structured universe. After that, the cosmos enters a state of near total simplicity. And yet, even in this quiet ending, there is something steady about it. The laws of physics still apply. Space still expands. Time still flows. Though what flow means in a universe where almost nothing changes is a deep question. The universe does not crash. It does not shatter. It fades. And this fading, stretched across timescales beyond imagination, may be the final chapter in the heat-death scenario. But there are still more possibilities to consider, because even matter itself, the protons inside atoms, may not be permanent. And if that is true, then the quiet future after the last black hole evaporates becomes even more sparse, even more empty, even more still. Up to this point, we've imagined a future where stars die, galaxies fade, black holes evaporate, and what remains is a thin mist of particles drifting through an ever-expanding universe. But there is a deeper question hiding underneath all of this. Is matter itself truly permanent? When you touch a table, hold a cup, or feel your own heartbeat, you are interacting with atoms. Atoms are made of smaller particles, electrons orbiting a nucleus, and inside that nucleus are protons and neutrons. Protons are especially important. Every hydrogen atom, the simplest and most common element in the universe, contains a single proton. And hydrogen makes up most of the ordinary matter in the cosmos. For a long time, protons were thought to be completely stable, indestructible, the solid building blocks of matter. But some modern theories suggest that even protons may not last forever. This idea is called proton decay. So what does that mean? Proton decay is the possibility that a proton can slowly transform into lighter particles over an incredibly long time. It would not explode. It would not shatter dramatically. It would simply change, breaking apart into other particles. But if protons can decay, the timescale is astonishingly long. Current experiments suggest that if proton decay happens, the lifetime of a proton is at least 10 to the power of 34 years. That's a 1, followed by 34 zeros. To compare, the universe today is about 10 to the power of 10 years old. So we are talking about a time span at least 10 septillion times longer than the age of the universe so far. If 1 second represented 1 year, 10 to the power of 34 years would be longer than the time it would take to count every star in every galaxy, one by one, at 1 star per second, and then repeat that process many times over. It's difficult to even feel the size of that number. But here's why it matters. If protons are unstable, even slightly, then in the extremely distant future, all matter made of protons will eventually break down. White dwarfs, which are mostly made of carbon and oxygen nuclei containing protons and neutrons, would slowly disintegrate. Neutron stars might also transform over time, depending on how their particles behave. Even the atoms making up planets, rocks, and any remaining structures would dissolve. Imagine a mountain slowly vanishing, not eroded by wind or water, but disappearing at the particle level, 1 proton at a time. It would not crumble. It would simply fade. Of course, this process would be incredibly slow. Nothing noticeable would happen over billions or trillions of years. But over spans like 10 to the power of 34 years or more, the cumulative effect becomes total. Matter itself would not be permanent. So what would the universe look like then? After black holes evaporate, perhaps around 10 to the power of 100 years. And if proton decay is real, then over even longer timescales, most remaining matter would convert into lighter particles, electrons, positrons, neutrinos, and photons. The universe would become an even thinner soup of radiation and low-mass particles, scattered across distances so vast that interactions would be extremely rare. It's almost like taking a solid statue and letting it slowly dissolve into mist. Not visibly at first, but eventually completely. You might wonder, have we observed proton decay? So far, no. Large underground detectors, massive tanks filled with pure water, buried deep beneath mountains, have been built to watch for signs of proton decay. These detectors are about the size of cathedrals, holding tens of thousands of tons of water. Scientists monitor them carefully, looking for the faint signals that would indicate a proton breaking apart. But so far, none have been seen. That tells us that if proton decay happens, it is extremely rare. Maybe protons are truly stable. Maybe they last forever. We don't yet know, and that uncertainty changes the far future in subtle ways. If protons never decay, then some matter may survive indefinitely, though spread out and cold. If they do decay, then even the basic structure of matter will eventually vanish. Either way, the overall trend remains the same. Energy spreads out, entropy increases, structure fades. There's something quietly humbling about this idea. The atoms in your body, the protons in your cells, may outlast stars. They may drift through space, long after galaxies have dissolved. But even they may not be eternal. And yet for now they are stable. They form mountains. They form oceans. They form living beings capable of asking about the fate of the universe. In the grand timeline, we exist in an era of extraordinary structure. Matter clumps into stars. Stars form planets. Chemistry allows life. Far in the future, those layers of structure may be gone. But the path to that extreme simplicity is long and gradual. No sudden crash. No cosmic collapse. Just slow transformation over unimaginable stretches of time. And yet, not all possible endings are so gentle. So far, we've explored futures where the universe fades slowly, but there are other possibilities, more dramatic ones. What if dark energy does not remain steady? What if it grows stronger over time? In that case, the ending might not be a slow freeze, but a tearing apart of everything. So far, the future we've explored has been quiet. Stars burn out, galaxies drift apart, black holes slowly evaporate. A gradual fading. But what if dark energy does not stay gentle? What if it grows stronger over time? That possibility leads to one of the most dramatic endings scientists have imagined. It's called the Big Rip. To understand it, let's return to something simple. Right now, dark energy appears to act like a steady pressure built into space itself. As the universe expands, space grows and dark energy grows with it. But its strength per unit of space seems constant. But what if that's not true? What if dark energy increases as the universe expands? Not just in total amount, but in intensity. If that were the case, the expansion of the universe wouldn't just accelerate, it would accelerate faster and faster. Imagine stretching a rubber band. At first, you pull gently, then you pull harder, then harder still. Eventually, the tension becomes too much. It snaps. The Big Rip is like that, but on a cosmic scale. At first, the effect would be subtle. Galaxies already drift apart because of expansion. If dark energy strengthens, that separation would happen more quickly. Over billions of years, distant galaxies would disappear beyond the cosmic horizon faster than expected. But the real drama begins later. If dark energy continues increasing, it could eventually overpower gravity even inside galaxy clusters. Galaxies that were once bound together by gravity would begin to separate. Picture a cluster of grapes slowly drifting apart, each grape pulled away from the bunch. Then, as the strength grows, even individual galaxies could be torn apart. The stars orbiting within them would no longer be held tightly enough by gravity. Stars would drift away from their galactic centers. Next, solar systems would feel the strain. The gravitational bond between a star and its planets would weaken. Planets that have circled their stars for billions of years would spiral outward and drift into space. Imagine Earth slowly moving away from the Sun, not because of a passing object, but because space itself is stretching too strongly. And if dark energy keeps strengthening, eventually even the force holding planets together, the gravity binding matter into spheres, would be overcome. Planets would break apart, then stars themselves would be torn apart, their gas pulled outward, and in the final moments before the end, even atoms could be ripped apart. The electromagnetic force that binds electrons to nuclei, the force that makes chemistry possible, would be overwhelmed. Protons and electrons would separate, even atomic nuclei might disintegrate. Space would expand so violently that nothing could remain bound. Everything would be torn down to fundamental particles, and then those particles would be pulled apart as well. The timing of such an event, if it were to happen, depends on how dark energy behaves. In some theoretical models, the Big Rip could occur tens of billions of years from now, perhaps 20 or 30 billion years after the present. To put that in perspective, the universe is currently about 13.8 billion years old. So the Big Rip, in such a scenario, would happen in roughly the same amount of time as has already passed since the Big Bang. If one human lifetime were 1 minute, the universe's current age would be about 2.5 minutes. The Big Rip might come around 5 minutes, but it's important to pause here. Current observations suggest that dark energy behaves very close to a cosmological constant, steady and unchanging. There is no strong evidence yet that it is increasing in strength. The Big Rip is a possibility, not a prediction. Still, it's fascinating to consider. Unlike the heat death scenario, which is slow and quiet, the Big Rip would be sudden at the end. Once dark energy dominates over all other forces, the final stages would unfold rapidly. In the last few million years before the Rip, galaxy clusters would dissolve. In the last few months, solar systems would break apart. In the last minutes, planets would disintegrate. In the final fractions of a second, atoms themselves would be torn apart. Everything, from the largest cosmic structures to the smallest building blocks, would be pulled away by the accelerating expansion of space. And then there would be no structures left, just rapidly expanding space and isolated particles rushing away from one another. It sounds dramatic, almost like a cosmic storm that never stops growing. But remember, this depends entirely on the behavior of dark energy, and so far, the best measurements suggest that dark energy is steady. Still, we cannot measure its behavior perfectly. Our observations are limited to the part of the universe we can see, and that visible region is about 93 billion light-years across, so wide that even light, traveling fast enough to circle Earth 7 times in a second, takes billions of years to cross it. Beyond that horizon, we cannot see, so we don't yet know with certainty how dark energy will behave in the far future. For now, the Big Rip remains one possible ending, a more dramatic one, but not the only alternative to heat death. Because before dark energy was discovered, scientists considered a very different future, one where gravity eventually wins. Instead of being torn apart, the universe might collapse back inward. Before dark energy entered the picture, many scientists imagined a very different ending for the universe. Not a slow fading, not a violent tearing apart, but a grand reversal. It was called the Big Crunch. To understand it, Let's go back to that simple image of throwing a ball into the air. If you toss a ball upward, it rises for a while. Gravity slows it down. Eventually it stops. Then it falls back toward you. For much of the 20th century, scientists thought the universe might behave in a similar way. The Big Bang sent everything expanding outward. Galaxies drifted apart. Space stretched, but gravity, the pull between all matter, never stopped acting. Every galaxy pulls on every other galaxy. Every cluster pulls on neighboring clusters. The entire universe is laced with gravitational attraction. So the question was simple. Is there enough matter in the universe for gravity to eventually stop the expansion? If there were, then expansion would slow over billions of years. Galaxies would drift apart, more and more slowly. Eventually, the expansion would halt completely. For a brief moment, the universe would pause, balanced between outward motion and inward pull, and then it would reverse. Galaxies would begin moving toward each other. Distances would shrink. The temperature of space would begin to rise again. Picture a balloon that you inflate, then release. Instead of popping, it slowly deflates, shrinking back toward its original size. In the Big Crunch scenario, the universe would do something similar. As galaxies moved closer together, collisions would become more frequent. Over vast timescales, structures would merge, clusters would combine into larger structures. Eventually, everything would collapse inward. The sky, in that distant future, would look very different. Instead of distant galaxies fading away, they would grow brighter as they approached. The cosmic background radiation, which today is about 2.7 degrees above absolute zero, would grow warmer as space compressed. Temperatures would rise. Stars might ignite again as gas clouds were squeezed. And in the final stages, the entire universe could collapse into an extremely hot, dense state, perhaps similar to the conditions at the beginning. It's almost like rewinding a movie. Expansion becomes contraction. Cooling becomes heating. Structure collapses back into simplicity. And that leads to a natural question. If the universe collapsed back into a hot, dense state, could it explode outward again? We'll explore that idea next. But first, it's important to understand why the Big Crunch is now considered unlikely. The key factor is dark energy. When scientists discovered in the late 1990s that expansion is accelerating, the Big Crunch scenario lost much of its support. Instead of slowing down under gravity's pull, the universe appears to be speeding up. For gravity to win, dark energy would have to weaken or change behavior in the future. Right now, measurements suggest that dark energy makes up about 70% of the universe's total energy content. Matter, both visible and dark matter, makes up about 30%, and that balance favors expansion. To reverse expansion, the gravitational pull from matter would need to overcome dark energy's push. Imagine two teams in a tug-of-war. If one team is steadily growing stronger, while the other remains the same, the stronger team will win. At the moment, dark energy appears to be that stronger team. Still, there is uncertainty. Our measurements are precise, but not infinite. We can observe only the part of the universe whose light has reached us. Beyond that, we do not know. And even within our observable region, about 93 billion light-years across, we cannot measure dark energy's properties with absolute perfection. So while the Big Crunch is not favored by current evidence, it cannot be ruled out entirely. It remains a possibility if dark energy changes in ways we do not yet understand. There is also something deeply symmetrical about the Big Crunch idea. The universe began in a hot, dense state, smaller than an atom, yet containing all the energy and matter we see today. In that early moment, temperatures were trillions of degrees, hotter than the core of any star, by an unimaginable margin. If it were to end in a similar hot, dense collapse, the cosmic story would feel circular, beginning and ending in fire, expansion followed by contraction. There's something almost poetic about that symmetry. But even in a big crunch scenario, the collapse would not be sudden from our perspective. It would unfold over billions of years. Galaxies would slowly draw closer. The sky would grow brighter, not darker. The cosmic background radiation would warm. Time would still flow. Life, if it existed, might adapt to the changing conditions for a while. Eventually, though, as temperatures soared and densities increased, complex structures would not survive. The universe would become a dense, hot plasma once again. And at that point, we are left with a profound question. Is a collapse the true end? Or is it a beginning? Because if a collapsing universe reaches extreme density and temperature, could it bounce? Could there be another expansion? Another Big Bang? That idea leads us into one of the most intriguing possibilities of all. A universe that does not end, but cycles. A universe that breathes in and out. A universe that might rise again from its own collapse. If the universe were to collapse in a big crunch, squeezing everything back into an extremely hot, dense state, an obvious question appears. Would that be the final end, or could something happen next? This is where the idea of the big bounce comes in. Instead of the universe ending in a permanent collapse, some theories suggest that the collapse could trigger a new expansion, another Big Bang. Imagine breathing in and out. Expansion is like the universe exhaling. Contraction is like inhaling. In this picture, the cosmos might move through cycles, expanding, collapsing, expanding again. But how could that work? To picture it, imagine compressing a spring. As you push down, the spring resists. The more you compress it, the stronger the resistance becomes. If released, it springs back outward. Now, gravity pulls matter inward during collapse, but at extremely high densities, far beyond anything we can recreate on Earth. The rules of physics may change. Quantum effects, which usually operate on tiny scales, could become dominant. Some theories suggest that when matter is compressed to near infinite density, quantum forces might prevent a true singularity, a point of infinite density. Instead of collapsing to an infinitely small point, the universe might reach a minimum size, perhaps far smaller than an atom, but not zero. And from that compressed state, it could rebound, a bounce. It's important to ask something natural here. Has this happened before? If the big bounce is correct, our universe might not be the first expansion. There could have been previous universes, earlier cycles, expanding and collapsing long before ours. Imagine a rubber ball bouncing on the floor. Each bounce represents a universe. After one expansion and collapse, the next begins. In such a scenario, time might stretch far beyond our current Big Bang. The Big Bang would not be the absolute beginning, just the latest bounce. But there are challenges. First, current observations show that the universe's expansion is accelerating because of dark energy. For a bounce to happen, expansion would need to slow, stop, and reverse into collapse. As of now, there's no clear evidence that this reversal will occur. Second, the physics at extreme densities, far beyond what we can test, remains uncertain. We don't yet have a complete theory that unites gravity and quantum mechanics. Without that, we cannot fully describe what happens at the very smallest scales of a collapsing universe. Still, some models attempt to solve these problems. Certain versions of quantum gravity suggest that space itself has a smallest possible size, like a fabric woven from tiny threads. If space cannot compress beyond a certain limit, then total collapse into a singularity may be impossible. Instead, maximum compression would be followed by expansion. To get a sense of scale, during the original Big Bang, the entire observable universe, which is now about 93 billion light-years across, may have been compressed into a region smaller than a single atom. Imagine taking something so vast that light takes billions of years to cross it, and shrinking it down to something smaller than a grain of dust. If that happened once, could it happen again? The Big Bounce idea is appealing because it avoids a final ending. There is no ultimate fade into darkness, no permanent freeze, no final tear. Just cycles, birth, expansion, aging, collapse, rebirth. It also raises a fascinating thought. If there were previous universes, could traces of them remain? Could subtle patterns in the cosmic background radiation, the faint glow left over from the early universe, hint at events from before our Big Bang? Scientists have searched for such signatures. So far, no clear evidence has emerged. Another question naturally follows. If the universe cycles, does each cycle look the same? Or does each new expansion create different laws of physics, different constants, different structures? Perhaps each bounce resets certain conditions. Perhaps some cycles produce universes where stars never form, others where expansion is too rapid for galaxies to grow. In our cycle, conditions allowed stars, planets, and life. That fact alone is remarkable. Still, the Big Bounce remains speculative. Current data leans more toward continued expansion driven by dark energy. But our understanding of dark energy is incomplete. If it changes over time, if it weakens or reverses, then contraction could become possible. And if contraction becomes possible, then bounce scenarios return to the table. There is something comforting about cycles. Seasons change. Day follows night. Tides rise and fall. We are used to rhythms. An endlessly cycling universe feels familiar in that way. But whether the cosmos breathes in and out, or stretches outward forever, remains uncertain. And beyond expansion and collapse, there is another possibility, one that is quieter, but deeply unsettling. Not a collapse, not a tear, but a sudden shift in the very fabric of reality itself. A change in the vacuum of space. A new kind of ending, hidden in the quantum structure of the universe. So far, every ending we've explored has followed a kind of logic. Expansion continues, and the universe freezes. Dark energy grows and everything tears apart. Gravity wins, and the universe collapses. Or perhaps it cycles through bounces. Each of these endings unfolds over vast stretches of time, billions, trillions, or far more years. But there is another possibility, and this one does not wait for the slow passing of ages. It could, at least in theory, happen at any moment. It is called vacuum decay. Now, the word vacuum might make you think of empty space, just nothingness between stars. But in physics, a vacuum is more than emptiness. It is the lowest possible energy state of space itself. Imagine a ball resting in a shallow valley. The valley represents a stable state. The ball can roll around slightly, but it stays within the valley. But what if that valley is not the deepest one? What if, beyond a small ridge, there is a much deeper valley? In that case, the ball is not in the true lowest state. It's in what physicists call a false vacuum. Stable for now, but not the absolute minimum. If something nudges the ball hard enough to push it over the ridge, it would roll down into the deeper valley, and everything about its position would change. Vacuum decay is based on the idea that our universe might be sitting in such a false vacuum. Stable, but not ultimately stable. If there exists a lower energy state of space, a true vacuum, then in theory a tiny region of space could randomly shift into that lower state through quantum effects. If that happened, it would create a bubble of true vacuum. And here is where it becomes dramatic. That bubble would not stay small. It would expand at the speed of light, not pushing through space in the usual way, but transforming space itself as it grows. Inside that bubble, the laws of physics could be different. The strengths of forces might change. The masses of particles might shift. Atoms as we know them might not be stable. In simple terms, everything could be rewritten. You might ask, something natural. Would we see it coming? No, because the bubble would expand at the speed of light, about 300,000 kilometers per second, fast enough to circle Earth 7 times in 1 second. Nothing can move faster than light, and nothing can warn us ahead of it. If such a bubble formed somewhere in the universe, it would sweep outward, and we would not know until it arrived. And when it arrived, the change would be immediate. There would be no time to react, no gradual warming or cooling, just a sudden shift in the underlying structure of reality. Now, it's important to say something calming. There is currently no evidence that vacuum decay is about to happen. It is a theoretical possibility based on certain interpretations of particle physics. The universe has existed for about 13.8 billion years, an enormous span of time, without showing signs of such instability. If our vacuum were highly unstable, it likely would have decayed already. Still, physicists study the properties of fundamental particles, like the Higgs boson, to understand whether our vacuum state is truly stable or only metastable, meaning stable for a very long time, but not forever. Current measurements suggest that our vacuum might be metastable. That means it could last far longer than the current age of the universe, perhaps trillions upon trillions of years, before any decay becomes likely. To put that into perspective, if the universe's age were 1 day, we would be only seconds after midnight. A metastable vacuum might last not just 1 day, but billions of years worth of days stacked together. So even if vacuum decay is possible, it may be unimaginably far in the future. Still, the concept is fascinating. Unlike the heat death, which fades slowly, or the big crunch which unfolds over billions of years, vacuum decay would be abrupt. One moment, the universe behaves as it always has. The next, the fundamental rules change. It's like discovering that the ground you stand on is not bedrock, but a thin layer above something deeper. Yet even here, there is a quiet humility. Our understanding of the vacuum comes from theories tested in particle accelerators, machines that smash particles together at energies higher than we can otherwise create on Earth. But those energies are still tiny compared to what existed in the early universe. So we are piecing together a cosmic puzzle from fragments. The possibility of vacuum decay reminds us that the universe's stability is not something we can take for granted at the deepest level. And yet, for billions of years, it has held steady. Stars have formed, galaxies have grown, life has emerged. Whatever the ultimate fate, it has not interrupted this long unfolding. And that leads us gently to another question. In all these possible endings, freeze, rip, crunch, bounce, decay, what happens to life? Could anything survive into the far future? Could intelligence endure long after the stars go dark? When we talk about the end of the universe, it's easy to focus on stars and galaxies. But there's another question that feels more personal. What happens to life? Right now, life on Earth depends on a steady flow of energy from the sun. Every second, sunlight warms the planet, drives weather patterns, powers plants through photosynthesis, and supports entire ecosystems. The sun releases more energy in 1 second than humanity has used in all of recorded history combined. And it has been shining for about 4.6 billion years. Without that steady flow, life as we know it could not exist. So if the universe heads toward a heat death, a slow cooling where stars burn out, what happens to living beings? At first, nothing changes. For billions of years, stars will continue to shine. Even as expansion accelerates, local galaxies remain bound together by gravity. The Milky Way and Andromeda will merge in about 4 to 5 billion years, around the same time our Sun begins its red giant phase. Life on Earth likely won't survive that transformation. When the Sun expands, its heat could strip away oceans and atmosphere long before it engulfs the inner planets. But that is only Earth's story. Life elsewhere if it exists, could persist around other stars. And over the next 100 trillion years, that's 100,000 billion years, new stars will continue forming from clouds of gas. Red dwarf stars, which are smaller and cooler than the Sun, burn their fuel extremely slowly. Some may shine for up to 10 trillion years. That's about 1,000 times longer than the Sun's total lifetime. If life can form around red dwarfs, and some scientists think it might, then the universe has an incredibly long window for biological activity. But eventually, star formation ends, gas runs out, new suns stop being born. So what then? Could advanced civilizations find ways to survive without stars? Some physicists have imagined that future beings might harness energy from black holes. When matter falls into a black hole, it heats up dramatically before crossing the event horizon. That infalling material can release enormous amounts of energy, more efficient than nuclear fusion. In theory, a civilization advanced enough could build structures to extract that energy. Picture enormous energy collectors orbiting a black hole, capturing radiation from glowing material spiraling inward. But even that source is temporary. Black holes eventually evaporate through Hawking radiation, though over time spans like 10 to the power of 100 years, far longer than the current age of the universe. There's also another idea. Even in a cooling universe, there will still be energy differences for a very long time. The cosmic background radiation continues to cool, but objects like white dwarfs and neutron stars will remain warmer than empty space for trillions upon trillions of years. A sufficiently advanced civilization might use those temperature differences to generate energy, much like a heat engine uses a hot reservoir and a cold reservoir to do work. The amount of available energy would shrink over time, but it wouldn't vanish immediately. So could life stretch itself across unimaginable spans? Perhaps. But there's a deeper challenge. Life depends not just on energy, but on complexity, on interactions, on structure. As the universe expands and matter spreads thinner, interactions become rarer. In the far future, stars will drift apart. Galaxies beyond our local group will disappear beyond the cosmic horizon. Eventually, only the merged remnant of the Milky Way and Andromeda, sometimes called Milkomeda, may remain visible. Future observers might look out and see only their own galaxy, unaware that billions once filled the sky. And as entropy increases, maintaining order becomes harder. Life, at its core, is a battle against entropy. Organisms take in energy to build and maintain structure. Without sufficient energy flow, complex systems break down. Imagine trying to keep a house warm in winter without any fuel. Eventually, the heat leaks away. In the very distant future, when energy gradients are minimal, sustaining life would become increasingly difficult. Still, some thinkers have proposed bold ideas. Perhaps life could slow its own perception of time. If energy becomes scarce, an advanced civilization might enter long periods of dormancy, waking briefly to use small amounts of energy efficiently. If one conscious experience today takes 1 second, maybe future beings could stretch that second across years or centuries, using less energy per thought. In a universe that cools gradually, there might be ways to adapt, but even the most optimistic scenarios face limits. If proton decay occurs, matter itself dissolves over timescales like 10 to the power of 34 years or more. If the heat death reaches near-perfect equilibrium, there will be no energy differences left to power processes. And if the Big Rip or vacuum decay happens, survival becomes impossible. So what is the fate of life? In most models, life cannot last forever, but it can last for an astonishingly long time. The era of active stars may continue for trillions of years, far longer than the time that has passed so far. Right now, we are living in a young universe. Life emerged on Earth within a few billion years of the Sun's formation. If life is common elsewhere, then the universe may be only at the beginning of its biological story. There may be civilizations yet to arise around long-lived red dwarfs. There may be minds that will exist when our sun is long gone. Still, even if life eventually fades with the stars, that does not make it small. For billions of years, atoms forged in ancient supernovae have arranged themselves into beings capable of wondering about the future of everything. That alone is extraordinary, and it leads naturally to another question. If stars fade and energy thins, could intelligence, in some form, outlive even the age of stars? Could thought itself endure in a cooling universe? As stars slowly burn out and the universe grows darker, it's natural to wonder not just about life, but about intelligence. Life is one thing: simple organisms, ecosystems, biological cycles. But intelligence adds another layer. It asks questions, it plans, it adapts. So could intelligence survive into the deep future, long after the bright era of stars has ended? To explore this, let's begin with something simple. Right now, your thoughts require energy. Your brain runs on chemical energy from food. That food ultimately depends on sunlight. Even fossil fuels, oil and coal, are ancient sunlight stored in chemical form. Without a steady flow of energy, the processes that support thought cannot continue. So, in a universe heading toward heat death, where energy becomes thin and evenly spread, intelligence would face a growing challenge. But intelligence by its nature seeks solutions. Some physicists have imagined that advanced civilizations could stretch their survival far beyond the lifespan of stars. One idea is energy efficiency. Today, human technology wastes enormous amounts of energy. We generate heat, lose energy through friction, and consume resources quickly. But a far future civilization might operate near theoretical limits of efficiency, using every available unit of energy carefully. There's a concept called the Landauer limit, which describes the minimum possible energy required to erase a bit of information. Even computation has a thermodynamic cost. In a cooling universe, intelligent beings might design systems that approach this minimum, squeezing as much thought as possible out of every bit of energy. Imagine living on a tiny battery, but stretching its charge for millions of years by using energy only when absolutely necessary. Another idea is slowing down subjective time. Let's think about this gently. If energy becomes scarce, perhaps intelligence does not need to operate at today's pace. Instead of thinking in seconds, it might think in years. If one thought today takes 1 second, a future mind might take a year to complete a single thought, but experience it internally as a normal pace. To an outside observer, it would seem almost frozen, but subjectively, it could feel continuous. It's like lowering the brightness of a screen to save battery life. As the universe cools, thought could slow. In this way, intelligence might stretch itself across trillions upon trillions of years, even as energy supplies dwindle. But there are limits. If the universe continues expanding forever, and entropy increases without bound, energy differences shrink without gradients. Hot and cold, dense and sparse, there is no way to extract useful work. Eventually, the battery runs down. There's also the challenge of isolation. As expansion accelerates, distant galaxies move beyond the cosmic horizon. Even today, some galaxies are already receding faster than light due to space expansion. Not because they are breaking physics, but because space between us is stretching so quickly. In the far future, only our local group of galaxies may remain visible. After that, even structures within galaxies disperse over immense timescales. Intelligence might find itself confined to smaller and smaller regions of matter, cut off from the wider cosmos. And yet, there is a kind of resilience in thought. Consider this. The universe today is about 13.8 billion years old. The first life on Earth appeared roughly 3.5 to 4 billion years ago. not long after the planet cooled enough to support it. Intelligence capable of science and reflection has existed for only a few 100,000 years, less than the blink of an eye in cosmic terms. If the universe allows for trillions of years of star activity, then intelligent life may just be getting started. There could be civilizations around red dwarf stars that will shine for 10 trillion years, about 1,000 times longer than the sun's lifespan. If even a fraction of those civilizations persist and adapt, intelligence could occupy a significant portion of the universe's luminous era. Some thinkers have even speculated about artificial intelligence not tied to biological limits, machines built to withstand cold, radiation, and time far better than organic life. Perhaps such systems could function at extremely low temperatures, using minimal energy. But even machines obey physics. They require matter. They require energy flow. If proton decay occurs and matter itself dissolves over timescales like 10 to the power of 34 years, structures, whether biological or artificial, cannot last forever. And if the universe reaches near-perfect thermal equilibrium, with temperature differences approaching zero, no process, not even computation, can continue. So can intelligence outlive the stars? Possibly, for a while. Perhaps for trillions upon trillions of years, beyond the current age of the universe. But in most models of cosmic fate, even intelligence eventually faces limits imposed by entropy and expansion. Still, it's worth pausing here. The fact that intelligence arises at all is remarkable. Atoms formed in the hearts of stars billions of years ago have assembled into beings capable of modeling black hole evaporation and vacuum decay in a universe 93 billion light-years wide, so vast that light takes billions of years to cross it. Small clusters of matter have become aware of the whole. Even if intelligence cannot last forever, its existence for even a fraction of cosmic time is extraordinary. And as we consider that far future, where stars fade, black holes evaporate, and matter thins, another question arises. If almost nothing changes, what does time even mean? In a universe where no events occur, where energy is evenly spread, does time still flow, or does it lose its meaning altogether? We often think of time as something steady. Seconds pass, minutes move forward, days turn into years. But what gives time its meaning? Why does it feel like it flows? Earlier, we touched on entropy, the idea that disorder increases. A glass falls and shatters. Ice melts in a warm room. Smoke spreads out in the air. We never see these processes reverse on their own. That direction, from order to disorder, gives us the sense of past and future. Entropy gives time an arrow. So what happens in a universe where entropy has nearly reached its maximum? Imagine the far future in the heat-death scenario. Stars have burned out. Black holes have evaporated. Matter, if it still exists, is spread thin across enormous distances. Temperature differences are almost gone. In such a universe, very little happens. Particles drift, radiation moves, but interactions are incredibly rare. Now pause and ask something gently. If nothing changes, does time still matter? Time, in physics, is often measured by change. A clock ticks because something moves. A pendulum swings. A quartz crystal vibrates. Electrons oscillate. If there are no meaningful changes, no processes unfolding, no differences evolving, what would a clock measure? Imagine a perfectly still ocean. No wind, no waves, no currents. If you sit and watch it, how do you tell that time is passing? You might check your watch, but the watch itself relies on internal processes, tiny oscillations powered by energy differences. In a universe at near perfect equilibrium, there would be no usable energy to power clocks, no heat flowing, no work being done. Some physicists suggest that in such a state, time would still exist mathematically, as a dimension in the equations of physics, but physically, it would lose meaning, because without change, there is no way to distinguish one moment from the next. Think of flipping through a book. If every page is identical, you cannot tell whether you are on page 1 or page 1000. The story does not move. In the far future of heat death, the universe may resemble that identical page, stretched across unimaginable scales. Still, quantum mechanics adds a subtle twist. Even in empty space, tiny fluctuations can occur. Particles can briefly appear and vanish. Over vast timescales, extremely rare events could still happen. For example, there is a strange idea called a Boltzmann brain, the hypothetical possibility that random fluctuations in a high-entropy universe could assemble particles into a brief, self-aware structure. The odds of such a thing are incredibly small, far smaller than winning a lottery trillions of times in a row. But given enough time, not billions or trillions, but numbers like 10 to the power of 100 years or more, even extremely unlikely events become possible. That leads to deep philosophical puzzles. If the universe lasts long enough, could random fluctuations produce brief islands of order? And if so, what does that say about time and observation? But even those rare events would be separated by vast stretches where nothing significant happens. Imagine waiting not minutes or years, but intervals so large that if 1 second represented 1 year, you would need longer than the current age of the universe just to count a tiny fraction of them. In such a universe, time stretches beyond intuitive meaning. There is also another layer to this question. As the universe expands, space grows larger and larger. Distant galaxies move beyond the cosmic horizon, the maximum distance from which light can reach us. Right now, the observable universe is about 93 billion light-years across. That's so wide that even light, traveling fast enough to circle Earth 7 times in a second, has needed billions of years to traverse it. In the far future, expansion will push more and more regions beyond reach. The observable universe will shrink. Eventually, observers in a galaxy may see only their own cluster. Later still, perhaps only their own stars. Time, as experienced by observers, will become more isolated. And after stars are gone, after black holes evaporate, and if proton decay occurs, there may be no observers at all. Without observers, without processes, without structure, does time flow? From the perspective of physical law, yes. From the perspective of experience, perhaps not. Time might continue in equations, but not in events. This idea can feel unsettling at first. We are used to movement, to change, to stories unfolding, but there is something peaceful about it too. The universe does not crash in this scenario. It does not scream. It simply relaxes into stillness, like a pendulum that has swung back and forth for trillions of years, gradually losing energy until it rests. And yet, even in that quiet state, the laws of physics remain. Space continues expanding, particles drift, quantum fluctuations whisper. Time, though stripped of drama, remains woven into the fabric of reality. For now, though, we are far from that stillness. We live in an era of change. Stars burn, galaxies collide, life evolves, and as expansion accelerates, something else is already happening. Something subtle but profound. The observable universe itself is shrinking, not in size, but in what we can see. Right now, when we look out into space with powerful telescopes, we can see galaxies billions of light years away. The observable universe, the part we can see, is about 93 billion light years across. That number sounds strange at first. The universe is about 13.8 billion years old, so how can we see something 93 billion light years wide? The reason is expansion. While light has been traveling toward us for 13.8 billion years, the space between us and those distant galaxies has been stretching the entire time. So by the time their light reaches us, those galaxies are much farther away than the simple age of the universe would suggest. It's like watching a car drive away while the road itself keeps lengthening. But here's the quiet, surprising part. Even though the universe is expanding, the portion we can observe will slowly shrink in the future. Not shrink in actual size. Space continues to expand, but shrink in terms of what remains visible to us. Because expansion is accelerating, dark energy is causing distant galaxies to move away faster and faster. Some galaxies are already receding so quickly that their light will never reach us. This doesn't break the speed of light rule. Those galaxies are not moving through space faster than light. Instead, space between us and them is expanding so rapidly that the total distance increases faster than light can cross it. Imagine standing on a treadmill that is speeding up. You try to walk forward, but the treadmill moves backward faster than you can walk. No matter how hard you try, you never reach the front. That's what is happening to light from some distant galaxies. As time passes, more galaxies will cross what is called the cosmic event horizon, a boundary beyond which events can never influence us. Today, we can see galaxies whose light has been traveling for billions of years. But in the far future, those same galaxies will fade. Their light will stretch to longer and longer wavelengths due to redshift. The stretching of space pulls their light into lower energy. Eventually, the light becomes so stretched that it is effectively undetectable. Over trillions of years, observers in our galaxy will see fewer and fewer distant galaxies. First, the most distant clusters will vanish, then nearer ones. Eventually, only galaxies gravitationally bound to ours, like Andromeda and other members of the local group, will remain visible. After the Milky Way and Andromeda merge in about 4 to 5 billion years, the resulting galaxy will be the dominant structure in our visible sky. Everything else will drift beyond reach. Picture standing on a shoreline at dusk, watching boats on the horizon. As night falls and fog rolls in, one by one, the boats disappear from view. They are still out there, but their light no longer reaches you. Future astronomers, perhaps trillions of years from now, might look up and see only their own galaxy. They would have no evidence of the vast cosmic web we see today. Right now, the universe is filled with enormous structures. Galaxies gather in clusters. Clusters connect in filaments stretching across hundreds of millions of light years, wide enough that if you tried to drive across one at highway speed, you would need longer than human civilization has existed. But in the far future, those filaments will not be visible. The cosmic microwave background, the faint afterglow of the Big Bang, currently at about 2.7 degrees above absolute zero, will also fade. As space expands, its wavelength stretches. Eventually, it becomes so long and so faint that it blends into the cold background. Without the cosmic microwave background, future observers would not even know the universe had a hot beginning. Without distant galaxies, they would not see evidence of expansion on large scales. They might conclude that the universe consists only of their single galaxy in an otherwise empty space. The deeper story of the cosmos would be hidden from them. It's a strange thought. Right now, we live in a privileged era, one where the universe is transparent and visible on the largest scales. We can measure expansion. We can detect the cosmic background radiation. We can observe galaxies billions of light years away. But this window is temporary. In perhaps 100 billion years, long before the heat death, the accelerating expansion will have pushed most galaxies beyond visibility. That number, 100 billion years, sounds immense. It's about 7 times longer than the current age of the universe. If the universe's age so far were 1 hour, that future point would be about 7 hours from now. But compared to the trillions and beyond that follow, it is still early. The shrinking of the observable universe does not mean space is collapsing. It means our horizon is changing. Light from distant regions will never catch up. And so, over time, the cosmos will appear smaller and lonelier. The vast city of galaxies we see today will become a single island, and eventually, as stars burn out, even that island will dim. The universe is not just expanding, it is isolating. And in that distant era, when only one galaxy remains visible, future observers may feel a profound sense of solitude. They may not know they are living in the fading afterglow of a once crowded cosmos. They may believe they are alone in an endless dark sea. And that brings us to another chapter of this story, the loneliest era of the universe. Imagine looking up at the night sky and seeing only a single galaxy. No faint smudges of distant clusters, no vast cosmic web stretching across billions of light years. Just one island of stars, surrounded by darkness. That may be the reality for observers in the far future. Right now, we live in what you might call a bright era of the universe. With modern telescopes, we can see billions of galaxies. Each one contains billions of stars. Some of those galaxies are so far away that their light began traveling toward us before Earth even formed. More than 4.5 billion years ago. When we observe them, we are looking deep into the past. But as expansion accelerates, that view slowly narrows. In about 100 billion years, roughly 7 times the current age of the universe, almost all galaxies outside our local group will have crossed the cosmic horizon. Their light will no longer reach us. They will not explode or disappear. They will simply fade from view as space stretches faster than their light can travel. By then, the Milky Way and Andromeda will have merged into a single large galaxy. Smaller neighboring galaxies will have been absorbed as well. The result will be one massive galaxy, a quiet remnant of what was once a crowded cosmic neighborhood. Observers living in that era may look up and see only stars belonging to that merged galaxy. They will not see distant galaxies receding. They will not detect the large-scale expansion. They may not even be able to measure the cosmic microwave background, the faint radiation left over from the Big Bang, because by then, its wavelength will have stretched so much that it becomes too weak to detect. Right now, that background radiation is about 2.7 degrees above absolute zero, around minus 270 degrees Celsius. In the far future, as expansion continues, it will cool further and stretch to wavelengths so long that it blends into near nothingness. Without that signal, there would be no clear evidence that the universe began in a hot, dense state. Think about what that means. We live at a time when the universe still carries clear signs of its origin. We can detect expansion. We can measure background radiation. We can see galaxies rushing away from us. Future astronomers may have none of that evidence. From their perspective, the universe might appear static and eternal, a single galaxy floating in darkness. They might conclude that their galaxy is the entire universe. It's almost like living on an island surrounded by thick fog, unaware that continents once stretched beyond the horizon. This period, long after most galaxies have vanished from view, could last for trillions of years. Stars will still shine for a while. Red dwarf stars in particular may continue burning for up to 10 trillion years, about 1,000 times longer than the sun's total lifespan. So life, if it exists in that distant era, may still look up at a sky full of stars. But those stars will all belong to one gravitationally bound structure. No distant galaxies, no cosmic expansion visible, no grand panorama. It will be the loneliest era of the universe, and yet it will not feel lonely to those who live within it, because they will not remember what came before. This idea carries a quiet lesson. Our view of the universe depends on when we live. Right now, the cosmos is still transparent and connected. We can see across vast distances, about 93 billion light years in diameter, because light has had time to travel. But that window is temporary. There was a time very early in the universe when it was opaque, filled with dense plasma, that blocked light. No one could have seen across it then. There will be a time, far in the future, when expansion hides most of it from view again. We live in a narrow middle period, a time when the universe is old enough to have structure, but young enough that distant regions are still visible. It's almost like standing on a hill at sunset, when the light is just right to see far across the landscape, before darkness closes in. Future civilizations might never know about dark energy. They might never detect the Big Bang. They might never realize that the universe was once filled with billions of galaxies. Unless they preserve records, echoes of earlier discoveries, the evidence may be gone, and that leads to something quietly profound. Cosmic knowledge is time-sensitive. The universe reveals different truths at different ages. Right now, it reveals a story of expansion and acceleration. In the loneliest era, it may appear quiet and unchanging. And far beyond that, when stars fade and black holes evaporate, it may appear almost empty. But here is the deeper question. Can we ever truly know which ending awaits? Heat death? Big rip? Big crunch? Bounce? Vacuum decay? Or are we forever limited by the boundaries of observation? That uncertainty is part of the story too. After exploring all these possibilities, the slow fading of heat death, the tearing force of the big rip, the collapse of a big crunch, the rhythm of a big bounce, the sudden shift of vacuum decay, a quiet question remains. Can we ever truly know which ending is correct? Science is powerful. We have measured the age of the universe to be about 13.8 billion years. We have mapped galaxies billions of light years away. We have detected the faint afterglow of the Big Bang, radiation cooled to just 2.7 degrees above absolute zero, colder than any natural environment on Earth by an enormous margin. We have discovered that the observable universe is about 93 billion light years across, so wide that if you tried to cross it at the speed of light, traveling fast enough to circle Earth 7 times per second, you would still need billions of years. These are astonishing achievements, and yet our knowledge has limits. We can only observe the part of the universe whose light has had time to reach us since the beginning. That boundary, the cosmic horizon, defines what we can measure. Beyond it, there may be more space, more galaxies, perhaps infinitely many, but we cannot see them. So when we try to predict the ultimate fate of the universe, we are working with incomplete information. Take dark energy. Right now, measurements suggest it behaves very much like a cosmological constant, steady, unchanging. That supports the heat death scenario, where expansion continues forever. But our measurements are not infinitely precise. We measure how galaxies move, we measure how light stretches, we build models that match observations. But even small uncertainties matter when projecting billions or trillions of years into the future. If dark energy changes slightly over time, even by a tiny fraction, the long-term fate could shift dramatically. It's a bit like forecasting the path of a leaf floating down a river. Over a few meters you can predict its motion fairly well. But over hundreds of kilometers, small variations in current can send it down completely different channels. We are trying to forecast not just thousands or millions of years, but spans like 10 to the power of 100 years. A 1 followed by 100 zeros. That is a scale so large that tiny unknowns grow enormous. There is also the question of physics itself. Our current understanding rests on two great frameworks: general relativity, which describes gravity and large-scale structure, and quantum mechanics, which describes the behavior of particles on tiny scales. Both work extraordinarily well in their domains, but we do not yet have a complete theory that unites them fully. A theory of quantum gravity at extreme conditions, like those near the beginning of the universe, or inside black holes, our current models break down. Without a complete theory, we cannot say with certainty what happens at those edges. Does a collapsing universe truly reach a singularity? Does a bounce occur? Is vacuum decay possible under the true laws of nature? We do not yet know. And then there is a deeper limit. The observable universe itself is changing. As expansion accelerates, distant galaxies move beyond our reach. Over time, evidence of the Big Bang will fade. The cosmic microwave background will stretch to wavelengths too long to detect. If we lived in the far future, in the loneliest era, we might not even know the universe is expanding. Our understanding depends on timing. We happen to live in an era when the universe is old enough to show structure, but young enough to reveal its expansion clearly. It's almost as if we arrived at just the right moment to see the clues. That does not mean we are special in a cosmic sense, but it does mean that knowledge is linked to perspective. So can we ever know the true ending? We can narrow the possibilities. We can measure dark energy's behavior with increasing precision. We can search for signs of proton decay. We can study black holes and quantum fields. We can build better telescopes, some placed in space, some deep underground, to gather more data. Each generation refines the picture, but absolute certainty about the far future may remain out of reach. Not because the universe hides it intentionally, but because the scales involved are so vast that direct testing is impossible. We cannot run an experiment lasting 10 to the power of 100 years. We cannot observe beyond the cosmic horizon. So we build models. We compare predictions with what we see. And we remain open to revision. There is something honest and calm about that. Science does not claim perfect knowledge. It moves closer and closer to understanding, adjusting as evidence grows. Perhaps future discoveries will reveal that dark energy changes over time. Perhaps we will find evidence that protons are unstable. Perhaps a deeper theory will unify gravity and quantum mechanics, clarifying the true path of cosmic evolution. For now, the best evidence points toward continued expansion and eventual heat death. But the universe has surprised us before. For centuries, we thought the cosmos was static. Then we discovered it was expanding. We thought expansion would slow. Then we discovered it was accelerating. So we proceed with humility. We listen carefully to what the cosmos tells us. And even if we cannot know the exact ending with perfect certainty, we can appreciate the remarkable fact that we can even ask the question. Atoms forged in ancient stars have assembled into minds capable of modeling futures trillions of years away. And that brings us to perhaps the most human question of all. If everything eventually ends, what does that mean for us? After traveling through billions, trillions, and even numbers like 10 to the power of 100 years, after imagining stars fading, galaxies drifting apart, black holes evaporating, and space stretching into stillness, we arrive at a quieter question. What does it mean for us? If the universe will one day grow dark and cold, if even matter itself may not last forever, does that make our lives small? It's natural to feel that way at first. When you compare a human lifetime, perhaps 80 or 90 years, to 13.8 billion years of cosmic history, it seems tiny. If the entire age of the universe were compressed into a single year, your lifetime would be far shorter than a blink of an eye. And yet, scale does not equal significance. A snowflake is tiny compared to a mountain. But its shape is intricate. Its existence is real. In the same way, our lives unfold within a narrow window of cosmic time. But within that window, something extraordinary has happened. The universe became aware of itself. Atoms formed in the cores of ancient stars. Stars that exploded billions of years ago now form your body. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were forged in stellar furnaces hotter than anything on Earth by millions of degrees. Those atoms traveled across space for unimaginable spans before becoming part of you. And now, arranged in just the right way, they ask about the fate of everything. That alone is astonishing. Yes, the universe may one day fade into heat, death, a quiet equilibrium where no more work can be done. Yes, distant galaxies will drift beyond view. Yes, stars will burn out. Yes, black holes will evaporate over timescales like 10 to the power of 100 years. Numbers so large that if 1 second equaled 1 year, you would need far longer than the age of the universe just to count a fraction of them. But none of that diminishes the present. In fact, it may deepen it. Think about a sunset. It lasts only minutes. The colors change, the light fades, and yet, because it is temporary, it feels precious. If the sky were permanently painted in sunset colors, we might stop noticing. Impermanence gives moments their intensity. The same may be true for existence itself. If the universe were eternal and unchanging, without beginning or end, would this moment feel as vivid? Perhaps knowing that stars do not last forever makes their light more beautiful. Perhaps knowing that life is rare and fragile makes it more meaningful. We live in what might be called the bright era of the cosmos. The universe is about 13.8 billion years old, still young compared to the trillions of years stars may continue shining. The night sky is filled with galaxies. The cosmic background radiation still whispers its origin story at 2.7 degrees above absolute zero. Faint, but detectable. We arrived at a time when the universe is still rich with structure and possibility. That timing is not something we chose. It is simply where we find ourselves. And within that window, we have curiosity. We build telescopes. We launch spacecraft. We send probes beyond our solar system. We measure expansion by watching galaxies drift away across distances of billions of light years. Distances so vast that light traveling fast enough to circle Earth 7 times per second takes billions of years to cross them. All of this from a small planet orbiting an ordinary star. It's easy to feel small in comparison, but small does not mean insignificant. A single neuron in your brain is tiny compared to your whole body, yet without it, your thoughts would be incomplete. Perhaps we are like that, small parts of a much larger system, yet meaningful within it. The universe may not care in a human sense. It follows physical laws. Gravity pulls, space expands, entropy increases. But meaning is not something the universe hands down from above. Meaning is something conscious beings create. When you look at the night sky and feel wonder, that feeling is real. When you ask questions about the beginning and end of everything, that curiosity is real. When you care about others, build relationships, create art, explore ideas, those experiences unfold within the vast cosmic timeline, and they matter because they are experienced. Differently fades. That does not erase what happens now. A song does not lose its beauty because it ends. In fact, its ending gives it shape. The same may be true for the universe. If there is a final chapter, whether a slow freeze, a tear, a collapse, or something we have not yet imagined, that does not make the story pointless. It makes this chapter unique. Right now, stars burn. Right now, galaxies shine. Right now, life exists. We are part of a universe that is dynamic and alive with change. Expansion continues. Space stretches. Light travels across billions of years to reach our eyes. And here we are, lying quietly, thinking about its fate. The universe may one day grow dark. It may cool until no stars remain. It may stretch until galaxies are isolated islands in endless space. It may even dissolve into near-perfect stillness. But for now, it burns, it glows, it evolves. And within it, for a brief and remarkable moment, consciousness awakens and asks, how will it all end? That question itself is part of the story. And for now, the story continues.